So, here's something worth thinking about as you settle in tonight. Right now, about 15 billion miles from where you're lying, there's a small metal object drifting through interstellar space. It weighs about as much as a grand piano, and it's moving at roughly 38,000 miles per hour, which sounds fast until you realize it has been traveling for almost 50 years and still hasn't reached the nearest star. It won't for another 40,000 years. That object is Voyager 1. It's the most distant thing humanity has ever built, and every single mile it has traveled, every signal it has sent back across that unimaginable distance, all of it traces back to an equation. A simple equation, written by hand on a piece of paper in a log cabin in rural Russia by a man who was almost completely deaf and who never built a rocket in his life. He figured out the math, he described the path, and then he waited, because the world didn't have the metal yet. The engines, the fuel, the guidance systems, the alloys that could survive the heat, none of it existed. The equation was ready. The engineering was about 100 years away. And that gap, that long, strange distance between having the idea and having the machine, turns out to be the thread that runs through the entire story of how human beings learned to leave this planet. It shows up again and again. Someone figures out what should be possible, writes it down, and then waits, sometimes for decades, sometimes for centuries, for someone else to come along and actually build the thing. The dreamers and the builders almost never turn out to be the same people, and the story of space exploration, when you really look at it closely, is the story of that handoff. The moment when the equation becomes metal, when the idea becomes fire, when the thing that lived only in someone's mind finally lifts off the ground and climbs into the sky. So here's what I want to do tonight. I want to walk you through that whole story, slowly, from the very beginning. We'll start with the first people who looked up and wondered what was out there. We'll follow the long, winding path through centuries of watching and thinking and calculating, through the first crude rockets and the mad geniuses who built them, through the terrifying politics of the Cold War and the space race it ignited, through the moon landings and the space stations and the robots we've sent to the edges of the solar system, all the way to the rockets landing themselves on floating platforms in the middle of the ocean right now, today, while you're lying here. And the question I want you to carry through all of it is this: how does a dream survive when the person who has it can't build it? What keeps an idea alive across generations, across borders, across wars, until finally, someone, somewhere, has the tools to make it real? And maybe the biggest question of all, what equations are sitting on someone's desk right now, waiting for metal that doesn't exist yet? There's no rush. This is a long story, and a good one. And if you drift off somewhere along the way, that's perfectly fine. The stars will still be there in the morning. Let's start where all of it starts, which is with looking up. Because before anyone dreamed of going to space, people spent thousands of years just trying to understand what they were seeing when they looked at the sky. And the remarkable thing is how much they figured out with almost nothing. No telescopes, no instruments, no math beyond basic geometry. Just their eyes, their patience, and a willingness to keep watching, night after night, year after year, scratching down what they saw. The ancient Babylonians, living in what's now Iraq, were doing this as far back as 1,800 years before the Common Era, maybe even earlier. They tracked the movements of Venus with astonishing precision, recording their observations in cuneiform script on clay tablets. And here's what made their work remarkable. They weren't just watching, they were predicting. They figured out that celestial events repeated in cycles, and they used those cycles to forecast what would happen next, when Venus would appear, when it would vanish, when eclipses would come,
That's data. That's pattern recognition applied to the cosmos, nearly 4,000 years ago. The Greeks pushed it further. Around 240 years before the Common Era, a man named Eratosthenes, the chief librarian at the Library of Alexandria, did something extraordinary. He measured the size of the Earth, and the way he did it was beautiful in its simplicity. He knew that at noon on the summer solstice in a city called Syene, far to the south, the sun shone straight down into a deep well, casting no shadow at the bottom.
But in Alexandria, that same moment, a vertical stick cast a shadow at an angle of about 7 degrees. He knew the distance between the two cities, roughly 500 miles. A little geometry, and he calculated the circumference of the Earth to within a few % of its actual value. No satellites, no telescopes, no computers. Just a stick, a well, and a sharp mind. And suddenly, the Earth had a size. It was a finite, measurable sphere, not an infinite plane stretching out forever. Once you know the Earth has a size, you can start wondering how big the space around it might be. Then there was Aristarchus of Samos, working around the same period, who proposed something genuinely radical: that the Earth goes around the Sun, not the other way around. He was right, but almost nobody believed him. The idea was too strange, too uncomfortable.
It would take roughly 1,800 years before Copernicus said the same thing, and another century after that, before Galileo aimed a telescope at Jupiter, saw its moons orbiting something other than Earth, and provided evidence that the sun-centered model was correct. Think about that timeline. Aristarchus had the right answer in the 3rd century BCE. The technology to confirm it didn't arrive until the 17th century CE. 2,000 years of the equation waiting for the instrument. And that pattern, the idea arriving long before the proof, is something you'll see over and over tonight. It might be the most important pattern in this whole story. But knowing what was up there, mapping the stars, measuring the Earth, understanding that planets orbit the Sun, all of that was still just observation. Looking at the sky as a thing to study, not a place to go. The shift from watching to reaching, from astronomy to aspiration, needed one more piece. It needed someone to describe, in precise mathematical terms, how objects actually move through space, how gravity works, what it would take to break free of it. That someone was Isaac Newton, and the piece he provided changed everything. In 1687, Newton published the Principia Mathematica, and buried inside that dense, brilliant book is a thought experiment that essentially invented the concept of orbital mechanics. He imagined a cannon on top of a very tall mountain, firing a cannonball horizontally. Fire it gently, and it arcs down and hits the ground nearby. Fire it harder, it travels farther before landing. But fire it hard enough, and something strange happens. The cannonball is still falling toward the Earth. Gravity hasn't stopped pulling on it, but the surface of the Earth is curving away beneath it at the same rate. The ball never lands. It just keeps falling, in a circle, around the planet forever. That's an orbit. That's what every satellite and space station is doing right now. Not floating, falling, just moving sideways fast enough to keep missing the ground. Newton gave humanity the math of motion through space. He showed that the same force pulling an apple from a tree is the same force keeping the moon circling the Earth. Gravity is universal. It works the same way everywhere, at every scale. And once you can write equations describing how objects move under gravity, you can start planning trajectories. You can ask, how fast would something need to travel to reach orbit?
How much energy would that require? What kind of engine could provide it? And there's a beautiful irony in all of this. Newton himself was deeply private, often petty, famously difficult to work with, and had no interest whatsoever in building machines. He was a mathematician and a philosopher.
The idea that his equations would someday be used to send human beings to the moon would have struck him as lunacy, quite literally. He described the physics of orbits as a thought experiment, not as an engineering blueprint. But thought experiments have a way of becoming engineering blueprints when enough time passes and enough stubborn people get hold of them. Kepler had gotten there first, in a sense. In the early 1600s, Johannes Kepler had worked out the laws of planetary motion, showing that planets move in ellipses around the Sun, not in perfect circles. His 3 laws described exactly how the speed of a planet relates to its distance from the Sun, how orbital periods relate to orbital sizes. Kepler had provided the shape of the road. Newton provided the reason it existed, gravity. Together, their work made it possible, for the first time in human history, to calculate exactly where a celestial body would be at any given moment in the future.
That's orbital mechanics. And it would eventually become the foundation of every trajectory ever calculated for a spacecraft. The answers to those questions wouldn't come for another 2 centuries. But Newton had drawn the map. He'd described the terrain. The road itself, the actual hardware that could take you there, would have to be built by people who hadn't been born yet, using fuels that hadn't been invented, in machines that nobody could yet imagine. The equation was on the table. The metal was 200 years away. But there was one technology that already existed, even in Newton's time, that would eventually close that gap. Rockets. Simple, crude, elegant rockets. And they had been around for a surprisingly long time, doing their thing in a completely different context, waiting for someone to look at them and see not a weapon, not a firework, but a ticket to the stars. The Chinese were using gunpowder-propelled rockets as weapons as early as the 13th century. During the siege of Kaifeng in 1232, the Jin dynasty reportedly used what were called fire arrows against Mongol invaders. Bamboo tubes packed with gunpowder mounted on sticks pointed at the enemy. They screamed through the air. They were wildly inaccurate. Sometimes they exploded before they left the launcher. But the principle behind them was sound, and it was the same principle that powers every rocket flying today. Newton's third law: every action has an equal and opposite reaction. Throw mass out the back and the rocket goes forward. It doesn't matter whether you're burning gunpowder in a bamboo tube or liquid hydrogen in a space shuttle main engine. The physics hasn't changed in 800 years. And here's what makes rockets special compared to every other form of propulsion we've invented. A car pushes against the road. A boat pushes water. A jet engine sucks in air, heats it, and blasts it backward.
Every one of those systems depends on having something external to push against. But in space, there's nothing. No air, no water, no ground. A rocket doesn't need any of it. It carries its own reaction mass, its propellant, and throws it backward. It pushes against itself. It's the only engine that works in a vacuum. Which is why, despite everything we've invented since the 13th century, rockets are still the only way to get to space. That fact was always there, embedded in the physics, waiting for someone to realize it. For centuries, nobody did. Rockets remained weapons and fireworks. Beautiful, dangerous, useful for scaring enemy soldiers or celebrating a festival. Nobody looked at a Roman candle and saw a vehicle for reaching the moon. That connection, the leap from gunpowder entertainment to interplanetary transport, required a different kind of mind. And the mind that made the leap belonged to a nearly deaf schoolteacher living in a wooden house in Kaluga, Russia. Working alone with pencil and paper, ignored by almost everyone around him. His name was Konstantin Tsiolkovsky, and the story of what he figured out in that quiet house is one of the most extraordinary chapters in the history of science. Because Tsiolkovsky didn't just dream about space travel, he did the math. He worked out the actual engineering requirements, the specific challenges, the precise relationships between fuel and mass and velocity that would govern every rocket that would ever fly. And he did it decades before anyone built anything that could get more than a few feet off the ground. Tsiolkovsky was born in 1857 in the village of Izhevskoy, about 120 miles southeast of Moscow. When he was 10 years old, a bout of scarlet fever took most of his hearing, and that deafness shaped everything that followed.
It isolated him from the social world, pulled him inward, into books, into his own thoughts, into a private landscape of ideas that turned out to be decades ahead of everyone else's. He couldn't attend regular school because of his hearing, so he educated himself, spending years in libraries, teaching himself physics, mathematics, astronomy, reading everything he could find. By his late 20s, he was working as a provincial school teacher, living modestly, and spending his evenings alone with calculations that would lay the theoretical foundation for all of spaceflight. In 1903, the same year the Wright brothers flew their first powered airplane at Kitty Hawk for 12 seconds, Tsiolkovsky published a paper called Exploration of Outer Space by Means of Rocket Devices. And in that paper, he derived the equation that now carries his name, the Tsiolkovsky rocket equation. It's one of the most important equations in aerospace engineering, and every rocket designer in history has wrestled with what it says. Here's what it tells you in plain language. The speed a rocket can ultimately reach depends on two things. First, how fast the exhaust gases leave the engine, and second, the ratio between the rocket's total mass when it's fully fueled and its mass when all the fuel is gone. That ratio is everything. And here's why it creates such a brutal constraint. Rocket fuel is heavy. If you want your rocket to go faster, you need more fuel. But more fuel means more weight. And more weight means you need even more fuel just to lift the extra fuel, which adds more weight, which demands more fuel. It's a vicious circle, and it means that for any given type of propellant, there's a practical ceiling on how fast you can go. Most of the mass of any rocket sitting on a launch pad is fuel. The actual payload, the thing you're trying to get to space, is a tiny fraction of the total weight. For a typical mission to low Earth orbit, the payload might be 2 or 3% of the rocket's total mass at liftoff. Everything else is fuel and the structure to hold it. Tsiolkovsky understood this deeply, and instead of being defeated by it, he proposed solutions. He described liquid-fueled rockets, which would be far more powerful and efficient than solid gunpowder. He proposed multi-stage rockets, where you build the vehicle in sections and throw away each empty section as its fuel runs out, so you're not wasting energy calling dead weight. He wrote about space stations, about airlocks, about the challenges of living in weightlessness. He even speculated about settling other planets. Think about what that means. A deaf schoolteacher in rural Russia, working with pencil and paper in a wooden house, described the basic architecture of space travel before anyone on Earth had built an airplane that could stay in the air for more than a few seconds.
He described multi-stage rockets 60 years before the Saturn V. He wrote about space stations 70 years before the first one flew. He imagined a future that his contemporaries couldn't begin to take seriously, and almost nobody noticed. His papers were published in obscure Russian journals, read by a handful of people. He lived in near poverty for most of his life. It wasn't until the Soviet government later adopted him as a national hero that his contributions were widely recognized. By then, he was an old man, frail and still nearly deaf, watching from a distance as the first generation of real rocket builders began turning his equations into hardware. Because that's the crucial thing about Tsiolkovsky. He was a theorist.
He never built a rocket. He never tested an engine. He never felt the ground shake under his feet as propellant ignited and thrust lifted a vehicle into the air. He gave the world the math, the vision, the theoretical roadmap. The equation was finished. The metal would have to come from someone else. And for a while, it seemed like nobody was listening. Tsiolkovsky's ideas sat in those obscure journals, waiting. Across the Atlantic, in a completely different world, a quiet American physics professor was about to pick up the thread, not because he'd read Tsiolkovsky's work, but because he'd arrived at many of the same conclusions independently. His name was Robert Goddard, and he was about to build the machine that Tsiolkovsky could only describe. Goddard was born in 1882 in Worcester, Massachusetts. He was a sickly child, frequently absent from school, and like Tsiolkovsky, his illness pushed him into reading and solitary thinking. He became fascinated with space travel after reading H.G. Wells's The War of the Worlds as a teenager, and one autumn day in 1899, at the age of 17, he climbed a cherry tree in his backyard and looked up at the sky and had what he later described as a kind of revelation. He imagined a device that could carry people to Mars. From that day forward, he said, his life had a purpose. He celebrated the anniversary of that moment every year for the rest of his life, calling it his anniversary day. But unlike Tsiolkovsky, Goddard didn't just think about rockets, he built them. After earning his doctorate in physics from Clark University, he began experimenting with solid-fuel rockets in the 19-teens, testing them in the basement of the physics building and on a farm outside of town. He was methodical, precise, obsessive about measurement. He proved experimentally that rockets could produce thrust in a vacuum, which sounds obvious now, but at the time was genuinely disputed. Plenty of smart people believed rockets needed air to push against, the same way a boat pushes water. Goddard showed they were wrong. In 1919, he published a paper through the Smithsonian Institution called A Method of Reaching Extreme Altitudes, in which he described the theoretical possibility of sending a rocket to the moon. The paper was serious, well-reasoned, and mathematically rigorous. The New York Times responded with an editorial mocking him. They wrote that Goddard didn't seem to understand basic physics, that he didn't grasp what every high school student knew, that a rocket couldn't work in a vacuum because there was nothing to push against. They suggested he lacked, and this is nearly a direct quote, the knowledge ladled out daily in high schools. The irony is almost painful, because Newton's third law, every action has an equal and opposite reaction, is precisely why rockets work in a vacuum. You push the exhaust one way, the rocket goes the other. You don't need air, you're pushing against your own exhaust. Goddard understood this perfectly. The New York Times did not issue a correction until July 17, 1969, the day after Apollo 11 launched for the moon, 43 years later. Goddard took the mockery hard. He became intensely private, reluctant to publish, reluctant to share his work with anyone outside a tight circle. This secrecy would become one of the quiet tragedies of early rocketry, because Goddard was doing groundbreaking engineering largely in isolation, and the wider scientific community barely knew about it. But he kept working, and by the mid-1920s, he had moved beyond solid fuels to something far more ambitious: liquid propellant. This was the key step. Solid rockets, the gunpowder kind, were simple but limited. You couldn't control the burn rate easily. You couldn't shut them off and restart them, and they didn't produce enough energy per pound of fuel to reach the speeds needed for space travel. Liquid propellants, burning a fuel like gasoline or kerosene with a separate oxidizer like liquid oxygen, could release far more energy and could be throttled, controlled, and managed in ways that solid fuels couldn't. Tsiolkovsky had described liquid fuel rockets on paper. Goddard was going to make one actually fly. On March 16, 1926, on his Aunt Effie's farm in Auburn, Massachusetts, Goddard and a small team set up a contraption that looked less like a rocket and more like something assembled from spare plumbing. It stood about 10 feet tall, held together by a frame that resembled a metal coat rack. The combustion chamber and nozzle sat at the top, not the bottom, because Goddard believed at the time that pulling the rocket from above would be more stable than pushing from below. He was wrong about that, but the basic principle was sound. The fuel was gasoline, the oxidizer was liquid oxygen. And on that cold March afternoon, with his wife Esther and a couple of colleagues watching from what they hoped was a safe distance, Goddard ignited the engine using a blowtorch on the end of a long pole. The rocket rose into the air. It flew for about 2.5 seconds. It reached an altitude of roughly 41 feet, about the height of a telephone pole. It traveled about 184 feet across the frozen field before crashing into a cabbage patch. 2.5 seconds, 41 feet. And that was the entire flight. But those 2.5 seconds changed the trajectory of human history, because what Goddard had just proved was that Tsiolkovsky's theory worked in practice. You could burn liquid fuel and liquid oxidizer together in a controlled chamber, direct the exhaust through a nozzle, and generate thrust. The equation had become metal. The idea had become fire. It wasn't much fire yet, just a few seconds worth, but it was enough. The principle was proven. Over the next 15 years, working mostly in isolation at a ranch near Roswell, New Mexico, funded partly by the Smithsonian and partly by grants arranged through Charles Lindbergh, who visited Goddard's workshop and immediately recognized what he was seeing, Goddard built increasingly sophisticated rockets. He developed gyroscopic stabilization systems to keep rockets flying straight. He invented vane-based thrust vectoring, using small deflectors in the exhaust stream to steer the rocket in flight. He experimented with fuel pumps, with different nozzle geometries, with cooling techniques to keep the combustion chamber from melting. By the mid-1930s, his rockets were reaching altitudes of over 1.5 miles. He filed more than 200 patents, and almost nobody in the American scientific or military establishment took him seriously. The Army came, looked at his work, shrugged, and left. The Navy showed mild interest and then moved on. Rockets seemed impractical, unreliable, dangerous, which they were, but that was the whole point of the research, to make them less so. And while Goddard was working in near obscurity in the New Mexico desert, something very different was happening across the Atlantic. Because the Germans were paying attention. Not to Goddard specifically, but to the same physics, the same dream, the same equations. And they were paying attention with resources and urgency that Goddard could never have imagined. A teenager named Werner von Braun had just joined a rocket club in Berlin, and within a decade, he would build a machine that would carry the dream of space travel into the darkest chapter of the 20th century. Here's where the story takes a turn that forces you to hold two completely contradictory ideas in your head at the same time. Because the technology that would eventually carry human beings to the moon was first developed at enormous scale, as a weapon of terror. And the man who led that development was one of the most talented, charismatic, and morally compromised engineers who ever lived. Werner von Braun was born in 1912 into an aristocratic Prussian family. His mother gave him a telescope when he was confirmed in the Lutheran Church, and that was the moment, by his own account, when space consumed his imagination. He was a terrible math student as a boy, but when he realized that mathematics was the language of rocketry, he attacked it with ferocious determination and became excellent. In his teens, he joined the Verein für Raumschifffahrt, the Society for Space Travel, a Berlin-based club of rocket enthusiasts inspired by the work of Hermann Oberth, a Romanian-born physicist who had independently derived many of the same principles as Tsiolkovsky and Goddard. Oberth's book, The Rocket into Planetary Space, published in 1923, had laid out the mathematics of spaceflight in rigorous detail. And unlike Tsiolkovsky's obscure Russian papers, Oberth's work was published in German, one of the dominant scientific languages of the era, and it found an audience. That audience included the German military. The Treaty of Versailles, which ended World War I, had imposed strict limits on German artillery. It specified ranges and calibers for guns, but it said nothing about rockets, because in 1919, nobody considered rockets to be weapons. The German army saw an opportunity. If they couldn't build bigger guns, maybe they could build guided rockets instead. And the enthusiastic young men at the Berlin Rocket Club were exactly the talent pool they needed. In 1932, the army recruited von Braun. He was 20 years old. By 1937, the operation had moved to a massive research facility on the Baltic coast called Peenemünde, and von Braun was its technical director at 25. With essentially unlimited military funding and thousands of engineers at his disposal, his team set about building a weapon that had never existed before. A long-range guided ballistic missile capable of delivering a warhead across hundreds of miles with no possibility of interception. The rocket they created was designated the A4. The world would come to know it by its propaganda name, the V2, short for Vergeltungswaffe 2, Vengeance Weapon 2. And from a pure engineering standpoint, the V2 was a genuine marvel. It stood about 46 feet tall and weighed nearly 28,000 pounds fully fueled. Its engine burned ethanol and liquid oxygen, producing roughly 56,000 pounds of thrust. It used a regenerative cooling system, circulating the fuel through a jacket around the combustion chamber before injecting it, carrying heat away from the walls so they wouldn't melt. The turbo pump that fed propellants into the engine was driven by decomposing hydrogen peroxide, generating steam to spin a turbine, an elegant solution that Goddard had experimented with years earlier, though the Peenemünde team likely developed it independently. The V2 had an inertial guidance system using gyroscopes and accelerometers to navigate its ballistic arc. It could reach altitudes of roughly 55 miles, above the boundary we now use to define the edge of space, and travel about 200 miles downrange at over 3,000 miles per hour. When it re-entered the atmosphere, it was moving faster than the speed of sound, which meant you couldn't hear it coming. There was no warning, no defense, just sudden, devastating impact. Beginning in September 1944, Germany launched more than 3,000 V2s at targets in England, Belgium, and France. They killed an estimated 9,000 civilians, and the production of the rockets was even more horrific than their use. The V2s were assembled in an underground factory called the Mittelwerk, carved into the Harz Mountains near Nordhausen, using forced labor from the Mittelbau-Dora concentration camp.
The conditions inside those tunnels were a nightmare beyond description. Prisoners worked with almost no ventilation, breathing toxic fumes, starved, beaten, worked until their bodies gave out. An estimated 20,000 people died producing the V2. More people were killed building the rocket than were killed by the rocket when it was used as a weapon. Von Braun knew. The degree of his personal involvement has been debated by historians for decades, but he held the rank of SS Major. He visited the Mittelwerk. He was aware of the labor source. After the war, he would spend his life insisting that he had been interested only in space travel, that the military work was a means to an end. "I aimed for the stars," he reportedly said. The satirist Mort Sahl added, "But sometimes I hit London." That's the contradiction at the heart of this part of the story. A man whose childhood dream was to explore the heavens built the machine that realized that dream on a foundation of extraordinary human suffering.
And the moral complexity of his legacy is inseparable from the history of space exploration itself, because without the V2, the trajectory of everything that followed would have been fundamentally different. The equation had become metal, but the metal was forged in darkness. And as the war ground toward its end in early 1945, that metal became the most sought-after prize on the planet, because both the Americans and the Soviets understood immediately that whoever controlled this technology would control the future of long-range weaponry, and potentially access to space. What happened next was a scramble, frantic, messy, morally questionable on all sides. In the final weeks of the war, von Braun organized the surrender of himself and roughly 120 of his top engineers to American forces. He chose the Americans deliberately, calculating that the United States was the country most likely to fund a space program. The US Army shipped them across the Atlantic under a secret program called Operation Paperclip, quietly whitewashing their wartime records to get around President Truman's directive that no active Nazis be admitted to the country. They brought along enough V2 components to assemble about 80 complete rockets. Von Braun and his team were set up at Fort Bliss, Texas, and the White Sands Proving Ground in New Mexico, where they spent the late 1940s launching captured V2s, training American engineers, and essentially teaching the United States how to build large rockets. The Soviets, meanwhile, captured the Mittelwerk factory, seized whatever V2 hardware and documentation the Americans hadn't already taken, and recruited, sometimes voluntarily, sometimes not, a number of German engineers who hadn't made it west. But the Soviet rocket program would ultimately be driven not by captured Germans, but by a homegrown genius whose story is, if anything, more harrowing than von Braun's and even more improbable. A man whose identity was kept so secret that for decades the outside world knew him only as the chief designer. His real name was Sergei Pavlovich Korolev, and before he became the architect of the Soviet space program, before he launched the first satellite and the first human being into orbit, he spent 6 years in the Gulag. Korolev was born in 1907 in Zhytomyr, in what is now Ukraine. Like von Braun, he was consumed by flight from a young age. He became an aircraft designer, then dove headlong into the excitement around rocketry in the early 1930s. He co-founded GIRD, the Group for the Study of Reactive Motion, the Soviet equivalent of the German amateur rocket clubs. His team launched the Soviet Union's first liquid-fueled rocket in 1933. He was brilliant, driven, exactly the kind of person the country needed. And then, in 1938, during Stalin's Great Purge, someone denounced him. That was all it took. He was arrested, interrogated, beaten so badly that his jaw was broken. Convicted in a sham trial on fabricated charges of sabotage and treason, he was sentenced to 10 years of hard labor and sent to Kolyma, in the far northeast of Siberia, one of the most brutal labor camps in the entire Gulag system. Winter temperatures at Kolyma dropped to 50 degrees below zero. Prisoners were worked to exhaustion mining gold in frozen earth. The death rate was staggering. Korolev arrived there as a 31-year-old engineer with a dream of reaching space, and he nearly died. He contracted scurvy. He lost most of his teeth. He was malnourished to the point of permanent heart damage. Somehow, through luck and the intervention of other imprisoned scientists who recognized his talent, he was transferred out.
He was moved to a sharashka, one of those peculiar Soviet institutions, a prison laboratory where jailed scientists worked on military projects under guard. Still a prisoner, but at least working on rocket and aircraft design instead of dying in a mine. He was released in 1944, but his conviction wasn't cleared for years. He carried that record and the damage to his body for the rest of his life. And yet, within a few years, this former Gulag prisoner with shattered health was handed the keys to the Soviet Union's most ambitious engineering project. The state that had nearly killed him put him in charge of building its future. If you wrote this as fiction, nobody would believe it. But it happened. And what Korolev did with that second chance would change the world in ways that nobody at the Kremlin fully anticipated. In 1945 and 46, Korolev traveled to Germany to study the V2 firsthand. He was deeply impressed, but he also saw its limitations clearly. He understood that copying the V2 wasn't enough. You had to absorb the engineering philosophy and then go beyond it. The Soviets did build a copy, the R1, as a starting point. But Korolev was already thinking much bigger. He wanted rockets powerful enough to reach orbit, rockets that could carry payloads across continents, rockets that could someday carry people into space. And here's what drove the urgency behind all of this. The context without which the rest of the story doesn't fully make sense. By the early 1950s, the Cold War had created a logic that was terrifying in its simplicity. Both the United States and the Soviet Union possessed nuclear weapons powerful enough to destroy entire cities. The question was delivery. How do you get a bomb from your territory to your enemy's territory before they can get theirs to you? Bombers could be intercepted. Submarines could be detected.
But a ballistic missile, a rocket that soared out of the atmosphere and re-entered at thousands of miles per hour on the other side of the globe, was essentially unstoppable with the technology of the era. There was no defense against it. You couldn't shoot it down. You couldn't outrun it. By the time radar detected the incoming warhead, you had minutes at most. So both superpowers poured resources into building intercontinental ballistic missiles, ICBMs, on a scale that dwarfed every previous rocket program combined. And the people who knew the most about large rockets, von Braun on one side and Korolev on the other, suddenly found themselves with budgets and political support they could never have dreamed of. The dream of space travel, for both men, was still the ultimate goal. But the path to space ran directly through the weapons programs. The same rocket that could deliver a nuclear warhead to Washington could, with minor modifications, deliver a satellite to orbit. The same engines, the same guidance systems, the same fuel. The dual-use nature of rocket technology was both a moral burden and a practical blessing. It meant that the money and urgency of the arms race would fund the technology of space exploration, whether anyone intended it to or not. Von Braun understood this. He played the game skillfully, publicly advocating for space exploration through articles, books, and television appearances, including a famous collaboration with Walt Disney in the mid-1950s that brought the concept of space stations and moon missions into American living rooms, while privately building army ballistic missiles and waiting for the moment when military hardware could be repurposed for the sky. Korolev understood it even more acutely. He'd spent years in the Gulag. He knew what the Soviet state could do to people who stopped being useful. As long as he was building weapons, he had political protection. And every weapon he built could also be a launch vehicle, if he could just get permission to use it that way. And here's where a peculiar technical detail created an enormous strategic consequence. In the early 1950s, Soviet nuclear warheads were heavier than American ones. The Soviets hadn't yet mastered the miniaturization techniques the Americans used. So Korolyev's intercontinental ballistic missile, the rocket the military wanted him to build, had to be powerful enough to loft a payload of several tons across intercontinental range. He needed to build something truly enormous. And the rocket he designed, called the R-7, was a masterpiece that would change history in ways its military sponsors never intended. The R-7 used a cluster approach. Instead of one massive engine, Korolev surrounded a central core stage with 4 strap-on boosters, each with its own set of engines, all burning kerosene and liquid oxygen. At liftoff, all the engines fired together, producing about 900,000 pounds of thrust. The boosters would burn out and fall away about 2 minutes into flight, and the core would continue accelerating the payload. This was staging, exactly what Tsiolkovsky had described in his 1903 paper, realized in Steel and Fire half a century later. The R-7 stood about 100 feet tall, weighed roughly 660,000 pounds, fully fueled, and was the most powerful rocket in the world when it first flew in 1957. The first test in May failed when a strap-on booster caught fire, but by August they had a successful flight. The R-7 traveled its full intercontinental range. The Soviet Union officially had a weapon that could strike the American homeland. But Korolev had been planning for something beyond weapons all along. He'd been quietly lobbying the Soviet leadership for permission to use the R-7, not just as a missile, but as a space launch vehicle. And because the R-7 was so powerful, designed to carry those heavy warheads, it had more than enough capability to put a small object into orbit around the Earth. On October 4th, 1957, a modified R-7 launched from the Baikonur Cosmodrome in the desert steppes of Kazakhstan. The payload was a polished aluminum sphere, about 23 inches across, weighing roughly 184 pounds. It had 4 trailing antennas and a simple radio transmitter that broadcast a steady beep on frequencies that any amateur radio operator in the world could receive. They called it Sputnik. The word means traveling companion in Russian, and when it reached orbit, everything changed. It's hard to overstate the psychological impact of Sputnik. Americans could go outside at dusk, look up, and see a tiny point of light moving steadily across the sky. A Soviet-made object circling the Earth every 96 minutes, passing over their homes, their cities, their military bases, and there was absolutely nothing they could do about it. The beeping signal was picked up by radio stations around the world and broadcast on the evening news. It was the sound of the future arriving. And for the United States, it was a shock that bordered on panic. If the Soviets could put a satellite in orbit, they could put a nuclear warhead anywhere on the planet. The technology was essentially the same. Sputnik wasn't just a scientific achievement, it was a strategic threat. A month later, Korolev struck again. Sputnik 2 launched in November 1957, carrying the first living creature into orbit. A stray dog named Laika, pulled from the streets of Moscow. And here, honesty matters. Laika's mission was one way. There was no plan to bring her back. The technology to deorbit and recover a spacecraft safely didn't exist yet. The official Soviet story for decades was that Laika survived about a week before being euthanized painlessly. The truth, which didn't come out until 2002, was that she died within hours of reaching orbit, probably from overheating and stress. The space race, for all its wonder, had real costs from the very beginning, not just in money and risk, but in lives that had no voice in the matter. The American response to Sputnik was initially humiliating. The US had its own satellite program, Project Vanguard, run by the Naval Research Laboratory, but it wasn't ready. Under enormous political pressure to answer Sputnik, they rushed a Vanguard rocket to the launch pad in December 1957. On live national television, it rose about 4 feet off the pad, lost thrust, settled back down, and exploded in a spectacular fireball.
The press called it Flopnik and Kaputnik. It was a national embarrassment, broadcast to the entire world. And this, finally, is where Wernher von Braun got his chance. He and his team at the Army Ballistic Missile Agency in Huntsville, Alabama, had been developing their own rocket, the Jupiter C, a direct descendant of the V-2. Von Braun had been arguing for months that he could put a satellite in orbit if the government would just let him try. After the Vanguard disaster, they said yes. On January 31st, 1958, a Jupiter C launched Explorer-1, America's first satellite, into orbit. And Explorer-1 wasn't just a beeping sphere. It carried a cosmic ray detector designed by physicist James Van Allen. And that instrument discovered the belts of charged particles trapped by Earth's magnetic field, now called the Van Allen radiation belts. America's first satellite actually did science, which was a meaningful counterpoint to the Soviet achievement. But Korolev kept pushing. First satellite, first animal in orbit. And now he was working toward the prize that would shake the world more than anything else. The first human being in space. The spacecraft he designed for that mission was called Vostok, which means east in Russian. Its design was elegant in its simplicity. The capsule was a sphere, the most straightforward shape for surviving re-entry, because a sphere's aerodynamic properties are the same regardless of its orientation. You don't have to worry about it tumbling or entering the atmosphere at the wrong angle. The heat shield covered the entire surface. Inside, there was room for one cosmonaut, life support systems, and enough supplies for about 10 days, though the planned missions would be much shorter. There was one detail the Soviets kept secret for years. During the final phase of descent, after the capsule had slowed in the atmosphere, the cosmonaut would eject from the capsule and parachute down separately. The Vostok came down hard, too hard for a person to survive inside it. So the cosmonaut bailed out at high altitude and floated down under a personal parachute while the empty capsule thudded into the ground under its own. This mattered for international records because the Fédération Aéronautique Internationale, the body that certified aviation and spaceflight records, required that the pilot land inside the vehicle. The Soviets concealed the ejection for years to protect Gagarin's record. Before putting a human aboard, they tested with animals. In August 1960, a Vostok prototype carried 2 dogs named Belka and Strelka into orbit, along with a rabbit, 42 mice, 2 rats, and some fruit flies. They all came back alive. First successful recovery of living creatures from orbit. The path to human spaceflight was proven. Before Gagarin's flight, the Soviets had been methodically testing the Vostok system, and the Americans had been working on their own human spaceflight program, Project Mercury. The approaches revealed everything about the 2 space programs' philosophies. The Soviet approach was centralized, secretive, and driven by a single visionary. Korolev made most of the critical design decisions himself, often overruling committees. The program's very existence was classified. Cosmonauts were not identified publicly before their flights. Failures were simply not reported. If a mission went wrong, it had never happened. This secrecy served a dual purpose. It protected military technology, and it allowed the Soviets to present an image of flawless competence to the world. Every mission the public heard about was a success, because the failures were invisible. The American approach was, by comparison, chaotic and public.
NASA announced its astronauts, the Mercury 7, with great fanfare in April 1959. They were all military test pilots, selected for their physical fitness, piloting skills, and engineering backgrounds. Their names and faces were everywhere: Alan Shepard, John Glenn, Gus Grissom, Scott Carpenter, Wally Schirra, Gordon Cooper, and Deke Slayton. Life magazine had exclusive access to their families. Their every training exercise was documented, and their failures were public too. Everyone saw the Vanguard explosion. Everyone saw the delays, the postponements, the scrubbed launches. This transparency was a disadvantage in the short-term propaganda war, but it would prove to be an enormous strength in the long run, because it built a culture of accountability that, despite its failures, ultimately made NASA's engineering more rigorous. The Mercury capsule was tiny, a pilot squeezed into a space barely larger than a bathtub, wearing a silver pressure suit, surrounded by instrument panels and switches. The capsule was launched on either a Redstone missile for suborbital flights or an Atlas missile for orbital missions. The Atlas was a converted ICBM with a skin so thin that it would collapse under its own weight if it weren't pressurized internally, like a balloon. Astronauts who flew on the Atlas were well aware that they were riding a pressurized metal balloon filled with liquid oxygen and kerosene into the sky. Alan Shepard's suborbital flight on May 5, 1961, lasted just over 15 minutes. He experienced about 5 minutes of weightlessness. It was a modest achievement compared to Gagarin's full orbit 3 weeks earlier, and Kennedy knew it. But John Glenn's orbital flight on February 20, 1962, 3 orbits in 4 hours and 55 minutes, was a turning point for American confidence. Glenn became a national hero, and his flight proved that an American could survive and function in orbit. During Glenn's mission, a sensor indicated that the capsule's heat shield might be loose. If it came off during re-entry, Glenn would be incinerated. Mission Control decided to leave the retro rocket pack attached during re-entry, hoping it would hold the shield in place, even though this hadn't been tested. The retro pack burned away during re-entry, but the heat shield held. Glenn splashed down safely. The sensor, it turned out, was faulty. The heat shield had been fine all along. But for several tense orbits, Glenn flew without knowing whether he'd survive the trip home. Mercury proved that Americans could get to orbit and back. But the capsule was too limited for anything more ambitious. It could carry one person, couldn't maneuver in orbit, and had no docking capability. Everything Apollo would require, rendezvous, docking, spacewalking, multi-person crews, was beyond Mercury's capability. That's what Gemini was for. The person Korolev chose was a 27-year-old fighter pilot named Yuri Gagarin from a small town west of Moscow. He had an infectious grin and a calm demeanor that impressed everyone who met him. And on the morning of April 12, 1961, he climbed into the Vostok 1 capsule atop a modified R-7 at Baikonur. The rocket Korolev had originally designed to carry nuclear warheads was about to carry a human being into orbit for the first time in history. As the engines ignited, Gagarin said, "Poyechali, let's go." In 108 minutes, he completed a single orbit of the Earth, traveling at roughly 17,500 miles per hour, seeing what no human had ever seen, the full curve of the planet, the thin blue line of the atmosphere, the blackness of space beyond. The re-entry was rough.
The service module failed to separate cleanly, and the joined spacecraft tumbled wildly for about 10 minutes before the connecting straps burned through in the heat and the capsule stabilized. Gagarin ejected at about 23,000 feet and parachuted to a field near the Volga River, where a farmer and her granddaughter found him. He told them not to be afraid. He was a Soviet citizen, he said, and he had come from space. The scoreboard was devastating for the Americans. First satellite, first animal in orbit, first human in orbit, all Soviet. The United States had managed exactly one suborbital flight, Alan Shepard's Mercury mission on May 5, 1961, just 3 weeks after Gagarin. Shepard went up, came down, spent about 15 minutes in the air, and never reached orbit. It was a success by American standards, a footnote by Soviet ones. And a young American president named John F. Kennedy was watching all of this with growing alarm.
The Cold War wasn't just about missiles and alliances anymore. It was about perception. Whichever system, democracy or communism, appeared more technologically advanced would win hearts and minds around the world. And right now, the Soviets were winning that argument decisively. Kennedy needed a response, something bold enough to change the narrative, something so audacious that the Soviet head start wouldn't matter. He consulted with his vice president, Lyndon Johnson, and with NASA leadership, and with von Braun himself. The question wasn't, what's the next logical step in space? The question was, what can we do that we have a genuine chance of beating the Soviets at? Low Earth orbit? The Soviets were already there. A space station? They could probably build one first. But the moon. The moon was so far beyond anything either nation had accomplished that it would essentially reset the race. Both countries would be starting almost from scratch, and the United States, with its vastly larger economy and industrial base, might actually have an advantage in a marathon rather than a sprint. On May 25, 1961, barely 6 weeks after Gagarin's flight, Kennedy stood before a joint session of Congress and delivered the line that would define a decade. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. When Kennedy spoke those words, the United States had exactly 15 minutes of human spaceflight experience. 15 minutes. Nobody at NASA knew how to rendezvous 2 spacecraft in orbit. Nobody knew how to build a rocket powerful enough to reach the moon. Nobody knew whether a human being could survive a week in space, let alone perform complex tasks on the lunar surface.
There was a genuine concern among some scientists that the moon's soil might be so fine and powdery that a spacecraft would simply sink into it. The engineering problems Kennedy was putting a deadline on hadn't been solved because nobody had ever needed to solve them before. The equation was clear. Get to the moon and back in 9 years. The metal to accomplish it didn't exist yet. Not the engines, not the alloys, not the guidance computers, not the spacesuits, not the procedures. All of it had to be invented from scratch. Tested, refined, tested again, and made reliable enough to stake human lives on. And the clock was running. But that impossible deadline turned out to be the most important engineering decision of the entire program, because it forced choices that might never have been made otherwise. And the first of those choices, the one that shaped absolutely everything that followed, was the question of how to actually get there. There were 3 approaches on the table.
The first was called direct ascent. Build one enormous rocket, fly it straight to the moon, land the whole thing on the surface, and launch it back off the moon to come home. Simple in concept, staggering in execution. This would have required a rocket called Nova, even bigger than what eventually became the Saturn V, and the engineering challenges of landing and relaunching that much mass on the moon were immense. The second approach was Earth Orbit Rendezvous. Launch multiple rockets, assemble or refuel a moon-bound spacecraft in Earth orbit, then send it on its way. Smaller individual rockets, but multiple launches for every mission, with all the timing and complexity that implied. The third option was the one that won, and it was championed by a NASA engineer named John Houbolt, who went so far as to write directly to the Associate Administrator of NASA, going over the heads of his own superiors, because he was convinced this was the only way to make the deadline, and he felt the bureaucracy was going to kill the idea. The approach was called Lunar Orbit Rendezvous, and when Houbolt first proposed it, a lot of people thought he was out of his mind. Here's how it works. You launch everything on one big rocket, but instead of landing the whole spacecraft on the moon, you leave the main ship, the command and service module, in orbit around the moon with one astronaut aboard. A smaller, lighter, purpose-built lander, the lunar module, detaches and carries two astronauts down to the surface. When they're done, the upper stage of the lunar module launches back up. Rendezvous with the orbiting command module, the crew transfers back, and they fly home.
It sounds more complicated than going straight down. And in terms of the number of steps, it is. Separation, descent, surface operations, ascent, rendezvous, docking. All of it happening at the moon, 240,000 miles from any help. If the rendezvous fails, the two astronauts in the lander are stranded. But here's the insight that made it brilliant. By not taking the entire spacecraft down to the surface, you drastically reduce the mass that has to land on the moon and launch off it again. The lunar module could be small and light, built for just 2 people. Thin walls, no heat shield because it was never coming back through an atmosphere. No need to be aerodynamic because there's no air on the moon. Every pound you save on the lander means less fuel needed to launch it off the surface, which means less weight, which means less fuel. And suddenly, the tyranny of Tsiolkovsky's equation is working in your favor instead of against you.
Lunar Orbit Rendezvous made it possible to do the entire mission with a single launch vehicle. And that vehicle was the Saturn V, designed by von Braun and his team at the Marshall Space Flight Center in Huntsville, Alabama. Let me take a moment with this rocket because it deserves it. The Saturn V remains, to this day, the most powerful rocket ever successfully flown. It stood 363 feet tall, taller than the Statue of Liberty. Fully fueled, it weighed about 6.5 million pounds. Its first stage, the SIC, was powered by 5 F1 engines. Each F1 produced 1.5 million pounds of thrust. 5 of them together delivered 7.5 million pounds of thrust at liftoff. The sound was something people described not as heard, but as felt, a physical pressure in the chest from miles away. Each F1 engine burned roughly 6,000 pounds of kerosene and liquid oxygen per second.
The turbopump feeding propellant into each engine generated more horsepower than all the engines on a Navy destroyer combined. And here's a detail that captures the kind of engineering persistence this program demanded. The F1 had a combustion instability problem. When you burn that much propellant that fast in a single chamber, you get pressure oscillations, waves of high and low pressure bouncing around inside. If those oscillations reinforce each other, they can tear the engine apart in milliseconds. Engines exploded on the test stand without warning. The solution was partly empirical. the engineers would deliberately set off small bombs inside the combustion chamber during testing to induce instability, then modify the injector plate design until the engine could damp out the oscillations and recover. They tested and modified hundreds of iterations until they had a design that was inherently stable. It was engineering by sheer persistence as much as by theory. The second stage, the S2, used 5 J2 engines burning liquid hydrogen and liquid oxygen, a more efficient combination, but far harder to handle, since liquid hydrogen has to be kept at -423 degrees Fahrenheit. The third stage, the S4B, had a single J2 engine and was the one that performed the translunar injection burn, the push that sent the spacecraft out of Earth orbit and toward the Moon. But while the Saturn V was being developed, NASA needed to teach its astronauts an entirely new set of skills. Rendezvous, docking, spacewalking, long-duration flight, navigation. And the program that did that teaching was Gemini, which flew 10 crewed missions between March 1965 and November 1966. 20 months. A new crewed spaceflight roughly every other month. The pace was extraordinary. There's something else worth pausing on about the Mercury and Gemini era, because it reveals how deeply the equation and metal tension ran, even within NASA. The original Mercury astronauts, all test pilots, fought hard for the capsule to have a window and manual controls. The initial engineering plan was to send them up as passengers, with the spacecraft controlled entirely from the ground. The astronauts objected. They weren't cargo, they were pilots. And they insisted on having the ability to fly the spacecraft themselves if the automatic systems failed. This tension between human control and automated systems would recur throughout the history of spaceflight, all the way to the touchscreen interfaces of Crew Dragon 60 years later. Every generation of spacecraft has grappled with the same question. How much do you trust the machine, and how much do you trust the human? The answer has shifted back and forth, but the question has never gone away. Deke Slayton, one of the original Mercury 7, was grounded before he ever flew due to a minor heart condition. He spent the next 16 years as chief of the astronaut office, selecting and assigning crews for every Gemini, Apollo, and early shuttle mission. He finally got his own spaceflight in 1975 on the Apollo-Soyuz test project at the age of 51. 16 years of watching other people fly the missions he'd helped plan, and then, finally, his turn. The equation of his career was written long before the metal of his mission was built. Let me slow down on the Gemini program for a moment, because the pace and ambition of what happened in those 20 months is genuinely hard to believe, and the lessons learned directly enabled everything Apollo would accomplish. Gemini 3, in March 1965, was the first crewed flight.
Gus Grissom, who had flown the second Mercury mission and very nearly drowned when his capsule sank after splashdown, commanded the mission with John Young. It was a short flight, just 3 orbits, but Grissom fired the thrusters to change the spacecraft's orbital path. That was a first for an American spacecraft, deliberately maneuvering in orbit rather than just riding whatever trajectory the rocket had put you on. The conceptual shift was enormous. You weren't a passenger anymore, you were a pilot. Then things moved fast. Gemini 4 featured Ed White's spacewalk in June 1965. He floated outside the capsule for about 20 minutes, tethered by a golden umbilical, using a handheld gas gun to push himself around. The Soviets had beaten them to it. Alexei Leonov had performed the first spacewalk 3 months earlier on Voskhod 2, though the Soviet mission had been far more harrowing than the public was told at the time. Leonov's suit ballooned in the vacuum, swelling so much that his hands slipped out of the gloves and his feet out of the boots. He couldn't fit back through the airlock. He had to partially depressurize his suit, risking decompression sickness to squeeze back inside. The Soviets reported it as a complete success. The details didn't emerge until years later. Gemini 5 set an endurance record, 8 days in orbit, proving that astronauts could function in space long enough for a round trip to the moon. Gemini 7 pushed that to 14 days, with Frank Borman and Jim Lovell crammed into a cabin the size of a phone booth for 2 straight weeks. They couldn't really move. They couldn't bathe. They wore the same clothes for the entire mission. It was physically miserable, but it proved the point. The human body could handle the duration of a lunar mission. And while Gemini 7 was still in orbit, NASA launched Gemini 6A, commanded by Wally Schirra, to rendezvous with it. On December 15, 1965, the 2 spacecraft flew in formation, approaching within a foot of each other. No docking, just station keeping. But it was the first time 2 crewed spacecraft had maneuvered to meet in orbit. The photographs of Gemini 7 seen through the window of Gemini 6A, 2 spacecraft floating together against the blackness of space, were among the most iconic images of the program. Gemini 8, in March 1966, achieved the first docking. Neil Armstrong and David Scott linked their capsule to an unmanned Agena target vehicle. But shortly after docking, the combined spacecraft began to roll. A stuck thruster on the Gemini was firing continuously, spinning them faster and faster. Armstrong undocked from the Agena, which made the problem worse because the lighter Gemini spun even faster without the Agena's mass to damp the rotation. They were approaching nearly 1 revolution per second. At that rate, the crew was minutes from losing consciousness. Armstrong shut down the orbital maneuvering system entirely and activated the re-entry thrusters, the backup system reserved for the return to Earth. He stabilized the spacecraft. The mission was cut short, but both astronauts were alive. Armstrong's cool under that kind of pressure didn't go unnoticed. 3 years later, when NASA was choosing who would command the first lunar landing, his performance on Gemini 8 was a significant factor. The later Gemini missions continued to push boundaries. Gemini 9A dealt with a docking target whose protective shroud failed to fully separate, leaving it looking like what the crew described as an angry alligator with its jaws open. Gemini 10 achieved a double rendezvous, docking with one Agena and then using its engine to fly to a second derelict Agena left over from a previous mission. Gemini 11 achieved a record altitude for a crewed spacecraft in Earth orbit, roughly 850 miles, high enough that the astronauts could see the curvature of the Earth's entire disk in their windows. And Gemini 12, the final mission, flown by Jim Lovell and Buzz Aldrin, solved the problem that had plagued nearly every previous spacewalk: exhaustion. Previous spacewalkers had struggled enormously with the physical demands of working in a pressurized suit in the vacuum of space. Every motion in a pressurized suit requires fighting against the stiffness of the fabric. It's like working inside an inflated balloon. Astronauts on earlier missions had returned to the cabin drenched in sweat, visors fogging, heart rates spiking. Aldrin, who had a doctorate in orbital mechanics from MIT and was methodical by nature, trained extensively underwater, using neutral buoyancy to simulate the resistance of working in zero gravity. On Gemini 12, his spacewalks went smoothly. He worked calmly, methodically, proving that with the right training and preparation, humans could perform useful work outside a spacecraft. That was one of the last major unknowns that needed to be answered before Apollo could proceed. When Gemini ended in November 1966, NASA had crammed an entire graduate education in spaceflight into less than 2 years. Rendezvous, docking, spacewalking, long-duration flight, orbital maneuvering, everything the moon missions would demand. The equation Kennedy had written, "Land a man on the moon before the decade is out," was looking more possible with every passing month. The metal was catching up to the deadline. Meanwhile, the Soviets were working on their own lunar program. Korolev was developing the N-1, a rocket even more ambitious than the Saturn V in some ways. But he was fighting bureaucratic battles, competing with rival designers for resources and political support.
And then, on January 14th, 1966, Korolev went into surgery for what was supposed to be a routine procedure. He was only 59, but his body had never recovered from the gulag. The broken jaw, the damaged heart, the scurvy. During the operation, complications arose. Sergei Korolev, the chief designer, the man who had launched Sputnik and sent Gagarin into orbit, died on the operating table. Korolev's death in January 1966 was more than the loss of a brilliant engineer. It was the loss of the one person in the Soviet system who had the authority, the respect, and the force of personality to hold the entire program together. Soviet space development was plagued by rivalries. Korolev had battled constantly with Valentin Glushko, the engine designer, over propellant choices. Korolev insisted on liquid oxygen and kerosene for the N-1.
Glushko favored storable hypergolic propellants and, when Korolev refused to use them, declined to build engines for the N-1. Korolev was forced to turn to a smaller design bureau led by Nikolai Kuznetsov, which produced the NK-33 engine. These engines were individually excellent, but the N-1's first stage required 30 of them, an unprecedented number, and the plumbing and control systems needed to manage 30 engines firing simultaneously proved to be the rocket's fatal weakness. The first N-1 test flight, in February 1969, failed 68 seconds after liftoff when a fire in the engine section triggered the automatic shutdown system. The second test, in July 1969, was worse. Just seconds after liftoff, a piece of debris was ingested by one of the engines, causing it to explode. The automatic system shut down all 30 engines, and the fully fueled rocket, all 4.5 million pounds of it, settled back onto the launch pad and detonated. The explosion was one of the largest non-nuclear blasts in human history. It destroyed the launch pad entirely and was visible from miles away. The Soviets rebuilt the pad and tried twice more, in 1971 and 1972. Both attempts failed. The program was quietly cancelled in 1974. The remaining N-1 hardware was scrapped, and for decades the Soviet Union denied the program had ever existed. If Korolev had lived, would the N-1 have succeeded? Nobody can say for certain. But it's telling that every major Soviet space achievement, Sputnik, Vostok, Voskhod, the early Soyuz missions, happened under his leadership, and the program's most spectacular failures happened after his death. He was the rare figure who combined engineering brilliance with political skill, someone who could design a rocket and also navigate the lethal bureaucracy of the Soviet state. When he was gone, the program fractured into competing factions, and the momentum that had once seemed unstoppable slowly bled away. But before all that played out, the American program was about to face its own darkest hour. And it happened not in space, not on a daring mission to the moon, but on the ground, inside a spacecraft that hadn't even left the launch pad. On January 27, 1967, the crew of Apollo 1, Gus Grissom, Ed White and Roger Chaffee, were inside their command module on the pad at Cape Kennedy, conducting a routine rehearsal test. The cabin was pressurized with pure oxygen at slightly above atmospheric pressure. Somewhere in the maze of wiring beneath their seats, a spark found something flammable. In a pure oxygen environment, fire doesn't just spread, it explodes. Flames raced through the cabin in seconds. The crew couldn't escape.
The hatch was a plug-type door that opened inward, held shut by the internal pressure. And even under normal conditions, it took about 90 seconds to open. In a cabin filling with flame and toxic smoke, 90 seconds was an eternity. All 3 astronauts died. The investigation found sloppy wiring, flammable materials throughout the cabin, and a hatch design that was essentially a death trap in a fire. NASA had been moving so fast, under so much pressure to meet Kennedy's end-of-decade deadline, that safety had been compromised in ways that were, in hindsight, inexcusable. The fire forced an agonizing 18-month pause in crewed Apollo flights. The command module was extensively redesigned. A new, quick-opening, outward-swinging hatch. A switch from pure oxygen at high pressure to a mixed nitrogen-oxygen atmosphere at launch. Removal of flammable materials. Improved wiring throughout. The redesigned Block 2 command module was a fundamentally safer spacecraft. Many engineers later said that without the fire and the redesign it forced, Apollo might never have successfully reached the moon. That's a terrible thing to say, knowing 3 men died. But it reflects a truth about engineering that repeats throughout this story. Sometimes the lessons that save the most lives are paid for at the highest cost. And it was in that atmosphere of grief and renewed determination that NASA accelerated. Apollo 7 tested the redesigned command module in Earth orbit, and then Apollo 8 did something breathtaking. In December 1968, Frank Borman, Jim Lovell, and Bill Anders flew all the way to the moon and back, orbiting it 10 times on Christmas Eve. The mission was partly a response to intelligence suggesting the Soviets were about to send cosmonauts around the moon. NASA took a gamble and leapfrogged straight to a lunar mission. Borman, Lovell, and Anders became the first humans to see the far side of the moon with their own eyes.
And on the 3rd orbit, Anders pointed his camera out the window and captured Earthrise, a photograph of our planet rising above the lunar horizon, small and blue and impossibly fragile against the blackness of space. That single image changed how people thought about the Earth itself. It became one of the most reproduced photographs in history. Apollo 9 tested the lunar module in Earth orbit. Apollo 10 was the dress rehearsal, taking the lunar module down to within about 9 miles of the lunar surface before pulling back. Tom Stafford and Gene Cernan flew so close they could see boulders and craters, the actual terrain where a landing might happen. Everything worked. The hardware was proven. The procedures were validated. The only thing left was to actually do it. And so, on the morning of July 16, 1969, a Saturn V stood on pad 39A at Cape Kennedy, fully fueled, ticking and creaking as super-cold propellants boiled off in the Florida summer heat.
Inside the command module Columbia sat 3 men. Neil Armstrong, commander, on the left. Michael Collins, command module pilot, in the center. Buzz Aldrin, lunar module pilot, on the right. About 1 million people had gathered along the beaches and causeways to watch. Hundreds of millions more watched on television around the world. At 9:32 in the morning Eastern Time, 5 F-1 engines ignited and the Saturn V lifted off. The first stage burned for about 2.5 minutes, pushing the vehicle to roughly 38 miles altitude and 6,000 miles per hour before separating and falling into the Atlantic. The S2 stage took over. After about 6 minutes, it separated too. The S4B third stage fired briefly to reach Earth orbit, and then, after 2.5 hours of system checks, it fired again for translunar injection, the burn that sent them on a 3-day coast to the moon.
During that coast, the spacecraft moved farther from Earth than almost any human beings had ever been. The Earth shrank behind them. The moon grew ahead. Inside the command module, about the interior volume of a large car, 3 people lived, ate, slept, navigated, and tried to stay calm about what they were about to attempt. On July 19th, they fired the service propulsion engine to enter lunar orbit. They spent a day orbiting, checking systems, studying the landing site through the windows. And then, on July 20th, Armstrong and Aldrin crawled through the tunnel into the lunar module Eagle, sealed the hatch, separated from Columbia, and began their descent. Collins stayed behind, orbiting alone. Every time he passed behind the moon, he was cut off from all radio contact with both his crewmates and the entire Earth. The loneliest person in the solar system. The descent is where the story gets tense. The guidance computer started throwing alarms during the approach. Program alarm 1202, then 1201. Executive overflow. The computer was being asked to handle more tasks than it could process simultaneously. In mission control, a 26-year-old guidance officer named Steve Bales had seconds to decide whether to call an abort. He'd studied these alarms. He knew that as long as they weren't continuous, the computer was shedding lower priority tasks and keeping the critical ones running. He called go. Flight Director Gene Kranz relayed the go. The descent continued. But there was another problem. Armstrong looked out the window and saw that the autopilot was steering them toward a boulder field on the rim of a large crater, not a safe place to land. He took semi-manual control, flying the lunar module forward, skimming over the rocks, searching for a clear spot. Fuel was running low. In mission control, Charlie Duke called out the remaining propellant. 60 seconds, then 30. At 30 seconds, they were moments from a mandatory abort. And then, Aldrin called out, "Contact light." A probe, dangling beneath one of the landing pads, had touched the surface. Armstrong shut down the engine. Eagle settled onto the moon with somewhere between 15 and 25 seconds of fuel remaining. "Houston, Tranquility Base here. The Eagle has landed." And Charlie Duke, his voice cracking. "Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again." Think about what just happened from an engineering standpoint. A vehicle designed and built by hundreds of thousands of people, launched from Florida on a column of fire, coasted 3 days across 250,000 miles of vacuum, entered orbit around another world, separated into 2 pieces, and landed on the surface of the moon with human beings inside. Every system had to work. The guidance computer, the radar, the throttleable descent engine, one of the first ever built. The reaction control thrusters, the life support, the communications, millions of parts. And the whole thing came down to a test pilot hand-flying the last few hundred feet, because the terrain wasn't what they expected. About 6.5 hours after landing, Armstrong opened the hatch and climbed down the ladder. It was July 20th, 1969, 10:56 p.m. Eastern Time. He stepped off the footpad and said the words, "That's one small step for man, one giant leap for mankind." He later said he'd intended to say, "a man," and some audio analysis supports that the "a" might be there, just lost in the static. Aldrin joined him about 20 minutes later.
They spent roughly 2.5 hours on the surface, collecting samples, planting a flag, setting up scientific instruments, taking photographs. And then they climbed back in, sealed the hatch, and rested before launch.
There was no backup. If it didn't fire, Armstrong and Aldrin would die on the moon. It fired. They launched off the surface, rendezvoused with Collins in Columbia, transferred back, jettisoned the Eagle, and headed home. On July 24th, the command module splashed down in the Pacific Ocean. The mission was over. The equation that Tsiolkovsky had written in his log cabin 66 years earlier had carried human beings to the surface of another world and brought them home. The equation had become metal, and the metal had touched the moon. Let me stay with Apollo 11 for another moment, because there's a detail about the mission that perfectly captures the theme of this whole story. The lunar module Eagle, the vehicle that landed on the moon, was built by Grumman Aircraft in Bethpage, New York. Its walls were so thin, about 12/1000ths of an inch in places, that a dropped screwdriver inside the cabin could have punctured the hull. The astronauts were separated from the vacuum of space by material thinner than a few sheets of heavy aluminium foil. The vehicle looked ungainly, all angles and gold foil and spindly legs. Nothing like the sleek, silver rockets of science fiction. But it didn't need to be sleek. It would never fly through an atmosphere. It only needed to work in the vacuum of space and the weak gravity of the moon. Every design decision on the lunar module came back to Tsiolkovsky's equation. Every pound saved on the structure meant less fuel needed to land and less fuel needed to launch off the surface. The ascent engine, the one that had to work perfectly with no backup, was deliberately kept as simple as possible. It used hypergolic propellants, chemicals that ignite spontaneously when they come into contact with each other. No ignition system needed. No spark plug that could fail. You open the valves, the propellants meet, combustion happens. It was as close to a guarantee as rocket engineering could offer, and it worked every time, on every mission. 6 lunar modules landed on the moon, and 6 ascent stages launched successfully off its surface. Not one failure. The command module, the capsule that brought the crew home, was its own engineering marvel. During re-entry into Earth's atmosphere at about 25,000 miles per hour, the heat shield on its blunt face reached temperatures of nearly 5,000 degrees Fahrenheit. The shield was made of an ablative material that charred and eroded away, carrying the heat with it. The temperature inside the cabin, a few feet away from that inferno, stayed comfortable. That's the kind of engineering precision the program demanded, life and death separated by inches of carefully designed material. And then there was the Apollo guidance computer, the machine that navigated the spacecraft and controlled the landing. It had less computing power than a modern calculator. Its memory was literally woven by hand, software encoded in copper wires, threaded through tiny magnetic cores by women working at a factory in Waltham, Massachusetts. They called it core rope memory, and it was indestructible once woven. You couldn't corrupt it with a power surge or a software glitch. The software itself was written by a team led by Margaret Hamilton at the MIT Instrumentation Laboratory. Hamilton's team designed the computer's software to prioritize critical tasks over less important ones, which is exactly what saved the Apollo 11 landing when those 12:02 alarms fired during the descent. The computer was overwhelmed, but it knew which tasks mattered most and dropped the ones that didn't. Hamilton later called this approach asynchronous processing with priority scheduling, and it became a foundational concept in software engineering. The code that landed humans on the moon was designed by a woman whose work, like Tsiolkovsky's equations, was far ahead of its time. The later Apollo missions expanded the scope of what was possible on the lunar surface dramatically. Apollo 12, in November 1969, demonstrated pinpoint landing accuracy, touching down within walking distance of the Surveyor 3 probe that had landed 2.5 years earlier. The crew actually retrieved parts of Surveyor to bring back for analysis, studying how the materials had weathered years of exposure to the lunar environment. When scientists examined the camera returned from Surveyor 3, they found bacteria, Streptococcus mitis, that appeared to have survived inside the camera housing on the Moon's surface for 2.5 years. Whether the bacteria were genuinely lunar survivors or post-recovery contamination has been debated for decades, but the finding raised fascinating questions about the hardiness of life.
Apollo 13, in April 1970, became the most famous failure in spaceflight history. 56 hours into the mission, an oxygen tank in the service module exploded. The crew, Jim Lovell, Jack Swigert, and Fred Hayes, lost most of their power, oxygen, and water. The command module was dying. Their only option was to use the lunar module, which was still attached, as a lifeboat. A spacecraft designed to support 2 people for 2 days on the lunar surface would have to support 3 people for 4 days on a modified trajectory around the Moon and back to Earth. Mission Control improvised. They figured out how to power up the command module's re-entry systems using the lunar module's batteries. They devised a procedure to build an adapter for the carbon dioxide scrubbers, using materials available on the spacecraft, cardboard, plastic bags, and duct tape, because the command module's square scrubber cartridges didn't fit the lunar module's round receptacles. The crew shivered in near-freezing temperatures as they conserved power. They swung around the far side of the Moon, closer to the lunar surface than any previous mission except Apollo 10, seeing the landing site they would never visit, and headed home. The re-entry was tense because nobody knew whether the heat shield had been damaged by the explosion. It hadn't. They splashed down safely. It was, as Mission Commander Lovell later said, a successful failure. No one reached the Moon, but everyone came home. 5 more Apollo missions landed on the lunar surface after Apollo 11. Apollo 12 made a pinpoint landing near the Surveyor 3 probe that had been sitting on the Moon for 2.5 years. Apollo 13, in April 1970, never made it to the surface. An oxygen tank in the service module exploded on the way to the Moon, crippling the spacecraft. The crew, Jim Lovell, Jack Swigert, and Fred Hayes, survived by using the lunar module as a lifeboat, nursing its limited power and oxygen for 4 days, while Mission Control improvised solutions from 200,000 miles away. They swung around the far side of the Moon and came home. It was the most successful failure in the history of spaceflight. Apollo 14 through 17 continued exploring the Moon with increasingly ambitious science. Apollo 15, 16, and 17 carried a lunar rover, an electric car that let astronauts range miles from the landing site. Apollo 15 found the Genesis rock, a chunk of the Moon's primordial crust, 4.5 billion years old. Apollo 17, the last mission, was the only one to carry a professional scientist, geologist Harrison Schmitt. Commander Gene Cernan and Schmitt spent 22 hours walking on the Moon, traveled 19 miles across its surface, and collected more data than any previous mission. On December 14, 1972, Cernan climbed back into the lunar module for the last time. Before he did, he said, "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." As of tonight, no human being has been back. And here's what's hard to explain to someone who didn't live through it: how quickly the world lost interest. By Apollo 13, the television networks had stopped carrying live coverage of the missions. They only resumed when the explosion turned it into a survival story. By Apollo 17, most Americans couldn't name the astronauts. Congress had been cutting NASA's budget since the late 1960s. The Vietnam War and the Great Society programs were consuming money and attention. The political motivation that had driven Apollo, beating the Soviets, was accomplished. The race was won, and once you've won a race, it's hard to convince people to keep running. The Soviet lunar program, without Korolev, and without a rocket that could fly, quietly collapsed. The N-1 was cancelled in 1974 after 4 consecutive failures. The hardware was scrapped. For decades, the Soviets denied they'd ever tried to go to the moon at all. In 1975, the Apollo-Soyuz test project, a joint American-Soviet mission, symbolically ended the space race. An Apollo spacecraft and a Soyuz capsule docked in orbit. The crews shook hands, and the Cold War competition that had driven humanity to the moon was, officially, over. Now I want you to hold 2 timelines in your mind for a moment, because the story is about to split, and both threads are equally important. On one side, while humans were racing to the moon and then figuring out what to do after, robotic spacecraft were being sent to places human beings couldn't yet go.
And on the other side, the question of how humans would sustain a permanent presence in space was being answered in a very different way than anyone expected. Both of these threads trace back to the same tension between equation and metal. The physics of interplanetary travel had been understood since Newton. The engineering to actually survive it, for a robot or a human, was a completely different kind of problem. Let me take the human thread first, and then we'll follow the robots. But before the Apollo hardware was completely mothballed, NASA found one more use for it. In May 1973, a Saturn V rocket, the last one that would ever fly, launched not a crew but a space station into orbit. It was called Skylab, and it was built from the empty upper stage of a Saturn V, converted into a habitable workshop.
The concept was ingenious in its economy. Take the enormous fuel tank of the S-4B stage, clear it out, install floors, walls, sleep compartments, a kitchen, an exercise area, and a solar telescope, and you have a space station roughly the size of a small house, already built and ready to launch in one piece. No orbital assembly required. Skylab got off to a rough start. During launch, a meteoroid shield tore away, taking one of the station's 2 main solar arrays with it and jamming the other one. Without the shield, the station's interior baked in direct sunlight, reaching temperatures of over 130 degrees Fahrenheit. The first crew, launched 11 days later aboard a smaller Saturn 1B rocket, had to perform an extraordinary repair. They deployed a parasol-like sunshade through an airlock to cool the station, then conducted a spacewalk to free the jammed solar panel.
It was improvisation on a grand scale, the kind of thing that would become a hallmark of human spaceflight. Something breaks, you figure out how to fix it with what you've got. 3 crews visited Skylab over the course of 1973 and 74, staying for 28, 59, and 84 days respectively. That last mission, 84 days, set a new record for the longest time humans had spent in space. The crews conducted experiments in materials science, Earth observation, and solar astronomy. They studied how the human body adapts to weightlessness, documenting the loss of bone density, the redistribution of fluids to the upper body, the changes in cardiovascular function. These were the first real data points on what long-duration spaceflight does to the human body, and they would inform every space station program that followed. Skylab was abandoned in February 1974.
The plan was for the shuttle, then under development, to eventually boost it to a higher orbit, or even refurbish it. But the shuttle came years late, and Skylab's orbit decayed. In July 1979, the station re-entered the atmosphere and broke apart over the Indian Ocean and Western Australia. Chunks of debris landed in the outback. The Shire of Esperance in Western Australia famously issued NASA a $400 littering fine. It went unpaid for decades, until a radio DJ finally raised the money and settled it in 2009. A year before Skylab fell, in 1975, the Apollo-Soyuz test project flew. An Apollo spacecraft and a Soviet Soyuz docked in orbit. American astronauts and Soviet cosmonauts shook hands through the hatch. It was a symbolic ending to the space race, and it was the last flight of an Apollo spacecraft. After that, for nearly 6 years, the United States had no way to put humans in space at all. The shuttle was still being built, and there was nothing else. The Soviets, meanwhile, took a different path after losing the moon race. Instead of chasing spectacular destinations, they focused on long-duration spaceflight in low Earth orbit. And they got very, very good at it, beginning with Salyut 1, launched in April 1971. The Soviet Union operated a series of increasingly capable space stations over the next 2 decades. The early Salyut stations were modest, roughly the size of a bus, with limited supplies and no way to be resupplied. Crews arrived in Soyuz capsules, stayed for weeks or months, and came home. Some missions were military in nature, designated Almaz stations, under a separate program focused on reconnaissance. Others were civilian scientific platforms. The living conditions were cramped and often unpleasant. The food was mediocre, and the psychological strain of spending months in a small metal tube with 1 or 2 other people, far from family, far from fresh air and sunlight, was immense. Some crews struggled. On Salyut 7, one crew reportedly became so frustrated that they took an unauthorized day off, refusing to follow the ground schedule. The psychological lessons learned on these stations would prove essential for everything that came later. But the real masterpiece of Soviet space station engineering was Mir, launched in February 1986. Mir, which means both peace and world in Russian, was the first modular space station, built piece by piece over a decade. A core module was launched first, and then additional modules, each with different functions, were sent up one at a time, docking to the growing complex. By the time it was complete, Mir had 6 modules, a total pressurized volume roughly the size of a 6-bedroom house. And it was the largest spacecraft in orbit. Cosmonauts lived on Mir for extraordinary durations. Valery Polyakov spent 437 consecutive days aboard, from January 1994 to March 1995, a record for continuous time in space that still stands. He was a physician, and part of his mission was to study himself, to document what more than a year in microgravity does to the human body. When he returned to Earth, he insisted on walking from the capsule under his own power, even though his body had spent more than 14 months adapting to weightlessness. It took enormous effort, and the footage shows him moving carefully, but he did it. He wanted to demonstrate that a human being could survive a trip to Mars and still function on arrival. Mir also became, unexpectedly, a symbol of international cooperation after the Cold War ended. As the Soviet Union dissolved in 1991, the Russian space program found itself desperately underfunded. A partnership with NASA provided both money and purpose. American astronauts began visiting Mir aboard the space shuttle, and later, living aboard for months at a time. The Shuttle Mir program, running from 1994 to 1998, was a crucial test of whether Americans and Russians could work together in space, sharing a station, sharing air and water and cramped quarters, learning each other's engineering philosophies and operational cultures. It wasn't always smooth. Mir was aging, and problems were frequent. In 1997, a fire broke out on the station,
and a few months later, a Progress supply ship collided with the Spectre module during a manual docking test, puncturing it and causing a partial depressurization.
The crew sealed off the damaged module and carried on. Living on Mir in its later years required a tolerance for duct tape, jury-rigged repairs, and occasional genuine danger. But the Shuttle-Mir partnership proved something essential: that the two largest spacefaring nations could cooperate on a shared platform. And that proof of concept was the foundation for the most ambitious construction project in human history: the International Space Station. The ISS was a political creation as much as an engineering one. After the Cold War, there was a strong incentive to give Russia's aerospace engineers something constructive to do, rather than having them sell their expertise to countries that might use it for weapons. The station brought together the United States, Russia, the European Space Agency, Japan, Canada, and other partners in a project so large that no single nation could have built it alone.
Assembly began in November 1998, when a Russian Proton rocket launched the Zarya control module, and a space shuttle flight delivered the Unity connecting node 2 weeks later. Over the next decade, the station grew piece by piece, module by module, truss segment by truss segment, assembled by astronauts and cosmonauts during more than 160 spacewalks. The shuttle's enormous cargo bay was essential to this process. Most of the American and European modules were too large to launch on any other vehicle. The station's solar arrays, which span the length of a football field, were unfolded and installed by spacewalking crews working in the vacuum of space in bulky pressure suits, using tools that had to be designed to work with thick gloves. Since November 2000, the ISS has been continuously inhabited. More than 2 decades of unbroken human presence in space.
Crews of 6, rotating every few months, living and working in a pressurized volume about the size of a 6-bedroom house, orbiting the Earth every 90 minutes, experiencing 16 sunrises and 16 sunsets every day. The science conducted on the station spans medicine, materials, biology, physics, and Earth observation. But perhaps the station's most important contribution has been simply proving that humans can live in space for extended periods, that the engineering of life support, recycling air and water, growing food, managing waste, maintaining physical and psychological health can sustain people for months or years at a time. The station is aging now. Cracks have appeared in some modules. Hardware designed for a 15-year lifespan has been in orbit for more than 25 years. Decommissioning is planned for around 2030, with the station to be deorbited in a controlled re-entry over the Pacific. Commercial space stations are being developed to take its place, operated by private companies like Axiom Space, which is already attaching modules to the ISS that will eventually detach and become an independent platform. But the end of the race left an uncomfortable question. What comes next? If you're not racing anyone, if there's no political urgency, if the public has moved on, how do you sustain a space program? The answer the United States came up with was a machine that would define the next 30 years of American spaceflight, for better and often for worse. A machine born from grand ambition, crippled by political compromise, capable of extraordinary things, and haunted by tragedy from beginning to end. And while humans were learning to live in orbit, robotic spacecraft were doing something arguably even more extraordinary. They were leaving the neighborhood entirely. The story of planetary exploration runs parallel to the human spaceflight story, and in many ways it's quieter, less dramatic in the moment, but staggering in what it has revealed about the universe we live in. It started early. Even before humans reached the moon, unmanned probes were being sent toward other worlds. The Soviet lunar program and the American Ranger and Surveyor programs sent spacecraft crashing into and eventually landing on the lunar surface in the 1960s, providing the close-up data NASA needed to confirm that the Moon's surface was solid enough to support a lander. The Surveyor probes, in particular, were crucial. Surveyor 1 soft-landed on the Moon in June 1966 and sent back over 11,000 photographs. When its mechanical scoop dug into the surface and the soil held firm, engineers at NASA exhaled. The Moon would support the weight of a lunar module. That was not a trivial concern. But the Moon was just the beginning. In December 1962, the Mariner 2 spacecraft flew past Venus, becoming the first successful interplanetary probe. It measured Venus's surface temperature, confirming that the planet was far hotter than anyone had hoped, roughly 800 degrees Fahrenheit, hot enough to melt lead. The romantic notion of Venus as a lush, tropical world beneath its clouds was dead. In July 1965, Mariner 4 flew past Mars and sent back 22 photographs that shattered another romantic notion. Mars wasn't the canal-covered civilization that science fiction had imagined. It was a cratered, barren, airless-looking world that resembled the Moon more than the Earth. Later missions would complicate this picture, revealing a planet with enormous volcanoes, vast canyons, and clear evidence of ancient water. But that first glimpse was a cold splash of reality. The two Viking landers, which touched down on Mars in 1976, were the most ambitious robotic missions of their era. Each one carried a suite of instruments designed to search for signs of life in the Martian soil. The results were ambiguous and fiercely debated. One experiment, the labeled release experiment, designed by Gilbert Levin, showed a positive result that looked tantalizingly like biological activity. But the other experiments found no organic molecules in the soil, which was hard to reconcile with the presence of life. The scientific consensus settled, uncomfortably, on the conclusion that the results were probably chemical rather than biological. Mars didn't seem to have life on its surface, but the question was far from settled, and it would drive Mars exploration for the next 5 decades. The grandest robotic missions of the 20th century, though, were the twin Voyager spacecraft, launched in the summer of 1977. Voyager 1 and Voyager 2 took advantage of a rare alignment of the outer planets that occurs only once every 175 years, allowing a single spacecraft to use the gravity of each planet to sling itself toward the next. This technique, called gravity assist, was another case of the equation preceding the metal by decades. The math of gravity assists had been worked out years before anyone had the engineering to attempt them. Voyager 2, in particular, performed one of the most extraordinary tours in exploration history. It flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. The only spacecraft ever to visit those last 2 planets. At each encounter, the images it sent back revealed worlds of stunning complexity. Jupiter's great red spot, a storm larger than the Earth, churning for centuries. The volcanic eruptions on Jupiter's moon Io, the first active volcanism found anywhere beyond Earth. Saturn's rings, resolved into thousands of individual ringlets. The bizarre terrain of Uranus's moon Miranda, which looks like it was shattered and reassembled at random. Neptune's great dark spot and the screaming winds of its atmosphere, the fastest in the solar system. And Triton, Neptune's largest moon, with geysers of nitrogen gas erupting from its frozen surface. Each of these discoveries was a gift, sent across billions of miles by a spacecraft about the size of a compact car, powered by a plutonium battery, navigated by a computer with less processing power than a modern key fob. The images took hours to travel from the spacecraft to Earth at the speed of light, arriving pixel by pixel, built up line by line like a fax from the edge of the solar system. Voyager 1, after its encounters with Jupiter and Saturn, was redirected onto a trajectory that would carry it out of the solar system entirely. In February 1990, as it crossed the orbit of Pluto, astronomer Carl Sagan persuaded NASA to turn the camera around and take one final photograph. The resulting image shows Earth as a tiny pale blue dot, less than a single pixel, suspended in a ray of scattered sunlight. Sagan wrote about it with a beauty that has rarely been matched in scientific prose. "Look again at that dot," he said. "That's here. That's home. That's us." Voyager 1 is still transmitting, more than 47 years after launch. In August 2012, it crossed the heliopause, the boundary where the solar wind gives way to interstellar space. The first human-made object to leave the solar system.
And strapped to its side, in a gold-plated copper record, is a collection of sounds and images from Earth. Greetings in 55 languages, music from Beethoven to Chuck Berry, the sound of wind and rain and a baby crying. A message in a bottle, tossed into an ocean so vast that the odds of anyone finding it are essentially zero. But someone built it anyway, and attached it to a spacecraft, and flung it toward the stars. The equation that Tsiolkovsky wrote in 1903, the one that says if you throw your exhaust fast enough and carry enough of it, you can reach any speed you want. That equation is what carried Voyager to the edge of everything we know. And the little spacecraft is still going, moving at about 38,000 miles per hour, carrying its golden record into the dark. That machine was the space shuttle. To understand the shuttle, you have to understand the moment it was born. In September 1969, just 2 months after Apollo 11 landed on the Moon, a group called the Space Task Group submitted a report to President Nixon outlining options for the future of NASA. The options were ambitious: a human mission to Mars, a permanent lunar base, a large orbiting space station, an Earth-to-orbit shuttle to service all of it, and one final option: discontinue human spaceflight entirely. Think about that for a moment. Just weeks after humanity's greatest exploration achievement, one of the options on the table was to stop. Nixon chose the modest path. No Mars, no moon base. An orbital infrastructure program centered on a reusable shuttle that would make access to low Earth orbit routine and affordable. That was the promise. The shuttle would fly frequently, maybe 50 or more times a year. It would carry astronauts and cargo to orbit and return, landing like an airplane, ready to fly again. The cost per launch would be a fraction of an expendable rocket. Spaceflight would become, if not routine, at least regular. That was the dream. The reality was a 30-year lesson in what happens when an engineering project is shaped more by politics than by physics. To understand why the shuttle ended up the way it did, you need to understand the series of compromises that shaped it, because each one seemed reasonable at the time, and together they produced a vehicle that was nobody's ideal design. The original concept, studied in the late 1960s and early 70s, was fully reusable. Both the orbiter and a large piloted booster would launch together, separate at altitude, and both would fly back to a runway landing. No expendable parts. That was the vision. An airplane-like space truck that could launch on Monday and fly again on Friday.
The problem was cost. Developing two fully reusable winged vehicles was estimated to cost about $10 to $12 billion, and the Nixon administration wasn't willing to spend that much. NASA Administrator James Fletcher was told to find a cheaper way. So the compromises began. First, the fully reusable booster was replaced by simpler options. A liquid-fueled flyback booster was studied, but found to be still too expensive. Then, solid rocket boosters were proposed. Solids were cheaper to develop, simpler in design, and could be manufactured by existing contractors. They had disadvantages, serious ones. A solid rocket, once ignited, burns until the propellant is gone. You cannot throttle it, and you cannot shut it down. If something goes wrong in the first 2 minutes of flight, while the solids are burning, your abort options are extremely limited. Engineers raised concerns about this. Some advocated strongly for liquid-fueled boosters, which could be shut down in an emergency, but the cost argument won. Next, the orbiter's internal fuel tanks were moved outside. Originally, the shuttle was supposed to carry all its propellant internally, like an airplane carries its fuel in its wings. But internal tanks took up space and added structural weight, reducing payload capacity. Moving the hydrogen and oxygen into a large external tank solved the payload problem, but sacrificed reusability for that component. The external tank was the only part of the shuttle system that was discarded after every flight, burning up during re-entry. At roughly $78 million per tank, it was the cheapest part to replace, but it was still a significant cost. The Air Force's involvement added another layer. The military wanted the shuttle to launch from Vandenberg Air Force Base in California into polar orbits, carrying spy satellites that weighed up to 40,000 pounds. And they wanted the ability to perform a single-orbit mission, deploying a satellite and landing back at Vandenberg after just one trip around the Earth. During that single orbit, the Earth would rotate roughly 1,000 miles beneath the shuttle. The vehicle needed enough cross-range capability, the ability to maneuver laterally during re-entry, to compensate for that offset and reach the runway. That requirement demanded large delta wings, which added weight and complexity and dictated much of the orbiter's aerodynamic shape. Ironically, the Air Force ultimately launched only a handful of military shuttle missions and never flew from Vandenberg at all. The shuttle launch pad, built there at enormous expense, was never used. Each compromise made sense in isolation. Together, they produced a vehicle that was partially reusable instead of fully reusable. More expensive per flight than projected, more dangerous than a clean sheet design would have been, and optimized for a military mission profile that was largely abandoned. The shuttle was, in a very real sense, designed by committee, and it carried the scars of every committee decision for its entire 30-year career. The original designs for the shuttle were fully reusable. Both the orbiter and its booster would fly back and land, just like airplanes. The orbiter would carry its own fuel internally. It was an elegant concept, but it was expensive to develop. And then the Air Force got involved. The military wanted to use the shuttle to launch spy satellites into polar orbit, and they had a specific requirement. The shuttle needed enough cross-range capability, the ability to maneuver sideways during re-entry, to perform a once-around mission. Go up, deploy a satellite, and come back down after a single orbit, landing back at the launch site even though the Earth had rotated over 1,000 miles beneath it during that orbit. That cross-range requirement killed the simplest reusable designs. It demanded large delta wings which added weight, which demanded more thrust, which demanded more fuel. The internal fuel tanks grew too heavy, so the fuel was moved outside into a large external tank that would be discarded after each flight. There went full reusability.
Then, to save development costs, the flyback liquid-fueled booster was replaced by two solid rocket boosters that would be recovered from the ocean and refurbished. Solid rockets were cheaper to develop, but they couldn't be throttled or shut down mid-flight. Once lit, they burned until the fuel was gone. That limitation would have consequences.
The shuttle that emerged from this process, designated Space Transportation System, first flew on April 12, 1981. Columbia, the first orbiter, launched from Kennedy Space Center with John Young, a veteran of Gemini and Apollo, in the commander's seat. The launch was extraordinary. The whole assembly, orbiter, external tank, solid boosters, produced about 7.5 million pounds of thrust at liftoff, comparable to the Saturn V. 2 minutes in, the solid boosters separated and parachuted into the Atlantic for recovery. The external tank was jettisoned just before orbit and burned up in the atmosphere. And Columbia, the orbiter, a spacecraft the size of a regional airliner, glided to a runway landing at Edwards Air Force Base in California. It was, by any measure, an astonishing piece of engineering. The shuttle could carry up to 8 crew members. It could deliver up to about 50,000 pounds of payload to low Earth orbit in its 60-foot-long cargo bay. It could bring payloads back from orbit, something no other launch vehicle could do. It could service satellites in orbit. It could serve as a platform for spacewalks, for science, for construction. And eventually, it would build the International Space Station, the largest structure ever assembled in space, piece by piece, over more than a decade of shuttle flights. But the shuttle never became what it was supposed to be. It never flew 55 times a year. The highest annual rate was 9 flights in 1985. The cost per launch never dropped to the levels promised. Each flight cost roughly $1.5 billion when you factored in the standing army of technicians needed to maintain and process the orbiter between flights. The thermal protection system alone, those thousands of heat-resistant tiles on the orbiter's belly, each one unique in shape, had to be individually inspected and often replaced after every mission. Reusability, in the shuttle's case, didn't mean easy or cheap. It meant refurbishment on a scale that rivaled building a new vehicle. And on January 28, 1986, the shuttle program faced its worst nightmare. 73 seconds after liftoff, the Space Shuttle Challenger broke apart over the Atlantic, killing all 7 crew members, including Krista McAuliffe, a high school teacher who was to be the first private citizen in space. Millions of schoolchildren were watching the launch live. The cause was a failure of an O-ring seal in the right solid rocket booster. The O-ring was a rubber gasket designed to prevent hot combustion gases from leaking through the joint between booster segments. On that January morning, the temperature at the launch site was 36 degrees Fahrenheit, well below the range at which the O-rings had been tested. The cold made the rubbers stiff and slow to seal. Hot gas burned through the O-ring, then through the external tank, igniting the liquid hydrogen inside. The whole assembly was torn apart by aerodynamic forces. What made Challenger especially painful was that the failure had been predicted. Engineers at Morton Thiokol, the company that manufactured the solid rocket boosters, had argued against launching in cold weather. They presented data showing that the O-rings performed poorly at low temperatures. They recommended delaying the launch. NASA managers overruled them. The launch had already been delayed multiple times, and there was pressure to maintain the flight schedule. The engineers were told to take off their engineering hats and put on their management hats. The launch proceeded. 7 people died. The shuttle program was grounded for nearly 3 years. When it returned, modifications had been made to the booster joints, and NASA's safety culture was, in theory, reformed. But the pattern of institutional failure proved hard to break. On February 1, 2003, the Space Shuttle Columbia was destroyed during re-entry, killing all 7 crew members.
The cause was a piece of insulating foam that had broken off the external tank during launch, 81 seconds after liftoff, and struck the leading edge of the orbiter's left wing, punching a hole in the reinforced carbon-carbon panels that protected the wing during the extreme heat of re-entry. When Columbia re-entered the atmosphere 16 days later, superheated plasma entered the wing through that hole, melted the aluminum structure from the inside, and the wing failed. The vehicle broke apart at about 207,000 feet, traveling at 18 times the speed of sound.
And here's what makes the Columbia disaster so haunting. Engineers at NASA had noticed the foam strike during the mission. They'd seen it on launch footage. They requested high-resolution imagery, possibly from military satellites, to assess the damage. NASA management declined the request. Foam had struck on previous flights without catastrophic results. Something dangerous had been happening regularly, and because it hadn't caused a disaster yet, it was reclassified from a safety concern to an acceptable risk. Until it wasn't. The Columbia Accident Investigation Board's report blamed not just the foam, but the organizational culture that allowed known dangers to be normalized. The shuttle flew for another 8 years after Columbia, completing the International Space Station. The last mission, STS-135, flew in July 2011. Atlantis landed at Kennedy Space Center, rolled to a stop, and the program was over. 135 missions, 2 catastrophic losses, 14 crew members killed. An extraordinary vehicle that never quite delivered on its founding promise. The shuttle's career, once it recovered from the Challenger disaster and resumed flying in September 1988, was defined by a series of genuinely remarkable missions, alongside the constant tension of operating a vehicle that everyone knew was more dangerous than it appeared. In April 1990, the shuttle Discovery deployed the Hubble Space Telescope into orbit. Hubble was one of the most anticipated scientific instruments ever built. A telescope above the atmosphere that could see the universe without the blurring and distortion of Earth's air. But when the first images came back, they were blurry. The primary mirror, ground with extraordinary precision, had been ground to the wrong shape. A flaw of about 2 microns, roughly 1/50th the width of a human hair, made the most expensive telescope ever built essentially nearsighted. The embarrassment was enormous. But the shuttle could do something no other launch vehicle could: go back and fix it. In December 1993, the crew of STS-61 flew to Hubble and, over 5 days of spacewalks totaling 35 hours, installed corrective optics, essentially a set of lenses that compensated for the mirror's flaw, along with new solar arrays and other upgrades. It was one of the most complex and ambitious repair missions ever attempted in orbit, and it worked perfectly. The images that came back after the repair were stunning, and Hubble went on to become one of the most productive scientific instruments in history, fundamentally changing our understanding of the age and expansion rate of the universe. The shuttle also carried the Space Lab module, a pressurized laboratory built by the European Space Agency that fit inside the cargo bay, turning the shuttle into a flying science platform. It deployed and retrieved satellites. It carried classified military payloads. And beginning in 1998, it began the construction of the International Space Station, a job for which it was uniquely suited. The station's largest modules, the American laboratory Destiny, the European Columbus Laboratory, the Japanese Kibo module. Each of these was the size of a school bus, and only the shuttle's cargo bay was big enough to carry them to orbit. Over the course of 37 shuttle missions dedicated to station assembly, crews installed modules, attached solar arrays that stretched the length of a football field, connected cooling lines, bolted together truss segments, and performed more than 100 spacewalks. The station's robotic arm, Canadarm2, built by the Canadian Space Agency, became essential to the process, grappling modules and moving them into position
with a precision that human hands alone couldn't achieve. By the time the shuttle retired, the ISS was essentially complete. A pressurized volume about the size of a 6-bedroom house, orbiting the Earth at roughly 17,500 miles per hour, continuously inhabited since November 2000. The shuttle program also gave us some of the most haunting near misses in spaceflight history. STS-27 in December 1988 suffered extensive damage to its heat shield tiles during launch, when debris from the right solid rocket booster struck the orbiter. The crew suspected they might not survive re-entry. When they landed safely, inspection revealed that over 700 tiles had been damaged, and one was missing entirely. The exposed area was saved only because it happened to be over a steel mounting plate, rather than the aluminium skin of the orbiter. If the tile had been missing from almost anywhere else, Columbia's fate might have come 14 years early. And that brings us back to the fundamental tension of the shuttle program. It was an extraordinary machine that could do things nothing else could. But it was also a machine that had been compromised at birth, its design distorted by political requirements that had nothing to do with optimal engineering. The Air Force's cross-range demand drove the Delta Wing, which added weight and complexity. The budget constraints drove the switch from a fully reusable system to a partially reusable one with an expendable tank. The solid rocket boosters, chosen for cost, couldn't be shut down in an emergency. The thermal protection system, thousands of individually shaped tiles, was labor-intensive to maintain. The cost per flight never dropped to the levels promised, and the flight rate never approached the ambitious projections that had justified the program's approval. 14 people died because of decisions that prioritized schedule and budget over engineering judgment. That's the shuttle's legacy, and it's one the aerospace industry has been trying to learn from ever since. But even while the shuttle was still flying, a different kind of revolution was beginning. One that would fundamentally change who builds rockets and how much it costs to reach orbit. And it started with a man who'd made his money selling software on the internet, who flew to Russia twice trying to buy old missiles, and who ended up building a rocket company in a warehouse near Los Angeles International Airport, because he thought the price of space travel was, quite simply, absurd. Elon Musk had co-founded PayPal and sold it to eBay in 2002 for about $1.5 billion, walking away with roughly $165 million after taxes. Instead of retiring, he decided he wanted to go to Mars. Literally. His original plan was modest. Put a greenhouse on the Martian surface, grow a plant in Martian soil, and beam the image back to Earth to reignite public enthusiasm for space exploration. So, he tried to buy a rocket. He flew to Moscow twice to negotiate for refurbished ICBMs, old Dnieper rockets left over from the Cold War. The Russians quoted him about $20 million per missile, and Musk thought the price was ridiculous. On the flight home from that second trip, according to the story that's been told many times, he opened a spreadsheet on his laptop and started calculating the raw cost of the materials in a rocket. The aluminium, the steel, the fuel, the avionics. He found that the materials cost roughly 2% of the price he was being quoted. 2%. The other 98% was overhead, inefficiency, cost-plus contracting, and decades of institutional inertia in the aerospace industry. That's when the plan changed. He didn't need to buy a rocket. He needed
to build a rocket company. SpaceX was founded in June 2002 in a warehouse in El Segundo, California. From the start, Musk's approach was different. He hired young engineers, many straight out of college, and told them to question every assumption. Why does this part cost this much? Why does it take this long to machine this component? Can we make it ourselves instead of buying it from a chain of subcontractors? The key insight was vertical integration. Instead of farming out hundreds of components to dozens of suppliers, each adding their own margins and delays, SpaceX would manufacture as much as possible in-house. Their own engines, their own avionics, their own structures, control the whole process. Their first rocket was the Falcon 1, a small two-stage vehicle designed to carry about 1,500 pounds to low Earth orbit. And the early years were brutal.
The first launch, in March 2006, from Kwajalein Atoll in the Marshall Islands, failed 25 seconds after liftoff. A corroded fuel line nut caused an engine fire. The second launch, in March 2007, reached space, but the upper stage failed to reach orbit. The third launch, in August 2008, was the one that nearly killed the company. The first stage performed perfectly, but residual thrust during stage separation caused the first stage to bump into the second. The payload was lost. 3 launches, 3 failures, and SpaceX was running out of money. Musk later said they had enough funding for one more attempt. If the 4th launch failed, the company was done. Everything SpaceX would eventually become, every Falcon 9 landing, every Dragon capsule, every crew mission to the space station, all of it depended on one more launch from a tiny island in the Pacific.
On September 28, 2008, the 4th Falcon 1 reached orbit perfectly. First privately developed liquid-fueled rocket to do so. Musk reportedly broke down in tears. Within weeks, NASA awarded SpaceX a $1.6 billion contract to fly cargo to the International Space Station. The company survived. And then, SpaceX did something that most of the aerospace industry thought was somewhere between impractical and impossible. They started landing their rockets. The idea wasn't new. A small experimental vehicle called the DCX had demonstrated vertical landing in the early 90s, but nobody had done it with an orbital-class booster, a first stage that had actually delivered a payload to orbit and then come back. The engineering challenge was enormous. You're taking a vehicle roughly 154 feet tall that's been traveling at several thousand miles per hour.
You need to flip it around, reignite its engines, guide it to a precise landing spot, and set it down on 4 legs with a single-shot final burn. The engine's thrust is greater than the near-empty stage's weight, so you can't hover. You get one chance. SpaceX failed repeatedly. Boosters came in too fast, too tilted, ran out of hydraulic fluid, tipped over on the landing barge, and exploded. They compiled the failures into a blooper reel they actually released publicly, which tells you something about the company's culture. But each failure taught them something. Each attempt got closer. On December 21, 2015, a Falcon 9 first stage landed vertically at Landing Zone 1 at Cape Canaveral. First time, an orbital-class booster had been recovered intact after delivering a payload to space. The first reflight of a recovered booster happened in March 2017. Within a few years, reuse became routine. Some Falcon 9 boosters have now flown more than 20 times.
A Falcon 9 launch costs customers around $67 million. Before SpaceX, a comparable launch might have cost $150 to $200 million. SpaceX cut the cost of reaching orbit roughly in half, and with booster reuse, their internal costs are even lower. In February 2018, SpaceX launched the Falcon Heavy for the first time, 3 Falcon 9 cores strapped together, making it the most powerful operational rocket in the world. The test payload was Musk's personal Tesla Roadster, with a mannequin in a spacesuit at the wheel. Absurd and theatrical. But the 2 side boosters landed simultaneously at Cape Canaveral in perfect synchrony, and the world watched, and even the skeptics had to admit it was breathtaking. On May 30th, 2020, SpaceX launched astronauts Doug Hurley and Bob Behnken to the International Space Station aboard Crew Dragon, the first crewed orbital mission from American soil since the shuttle's retirement 9 years earlier. During that gap, NASA had been buying seats on Russian Soyuz capsules at roughly $80 million per seat. The Crew Dragon mission was the first time a commercially built and operated spacecraft carried humans to orbit, and the capsule itself looked nothing like the spacecraft of previous generations. Sleek, with touchscreen controls replacing banks of physical switches. The entire rendezvous and docking with the station was automated, but commercial crew was just one thread. While SpaceX was landing boosters and NASA was buying rides, robotic explorers were quietly rewriting our understanding of the solar system. In August 2012, NASA's Curiosity rover touched down in Gale Crater on Mars, using a landing system so audacious the engineers called it the Sky Crane. The rover weighed about 2,000 pounds, too heavy for airbags, so the landing system entered the Martian atmosphere behind a heat shield, deployed a supersonic parachute, then dropped the heat shield, fired retro rockets to hover, and lowered the rover on cables, like a crate from a helicopter, setting it gently on its wheels. Then the descent stage cut the cables and flew away to crash at a safe distance. The whole sequence, from atmospheric entry to touchdown, took about 7 minutes. All of it autonomous, because the signal delay between Earth and Mars meant the rover had already either landed or crashed by the time anyone at the Jet Propulsion Laboratory knew the sequence had started. Curiosity found something remarkable in its first year. Clay minerals in the rocks of an area called Yellowknife Bay, minerals that only form in the presence of water that isn't too acidic or alkaline. The chemistry showed traces of sulfur, nitrogen, oxygen, phosphorus, carbon, the building blocks life requires. Curiosity hadn't found life, but it found that Gale Crater was once the bed of a freshwater lake billions of years ago, with conditions that would have been hospitable to microbes. The rover kept going. It has been operating for over a decade, far beyond its planned 2-year mission. Its successor, Perseverance, landed in Jezero Crater in February 2021, a site chosen because orbital images showed what looked like an ancient river delta. Perseverance carried more sophisticated instruments and a caching system to seal rock samples in titanium tubes for a future mission to bring back to Earth. It also carried Ingenuity, a tiny helicopter weighing about 4 pounds. Flying on Mars is absurdly difficult. The atmosphere is only about 1% as dense as Earth's. Ingenuity's blades had to spin at about 2,400 revolutions per minute to generate lift. On April 19, 2021, it lifted off the Martian surface, hovered at about 10 feet for 30 seconds, and landed. First powered, controlled flight on another planet. A small piece of fabric from the Wright brothers' flyer was attached to it. A quiet tribute connecting those 2 moments.
Kitty Hawk, and Mars. Ingenuity was designed for 5 flights over 30 days. It completed 72 flights over nearly 3 years. Farther out, the Cassini spacecraft spent 13 years at Saturn, from 2004 to 2017. And what it found at a tiny moon called Enceladus changed the way scientists think about where life might exist. Enceladus is small, about 300 miles across, small enough to fit inside the state of Arizona. But Cassini observed enormous plumes of water vapor and ice erupting from cracks near its south pole. Geysers shooting material hundreds of miles into space.
Flying through those plumes, Cassini detected water, salt, silica nanoparticles, and organic molecules. The silica was particularly telling. It indicated hydrothermal activity on the ocean floor. Hot water reacting with rock. The same chemistry that powers thriving ecosystems at hydrothermal vents in Earth's deepest oceans. Under its icy shell, Enceladus has a global ocean of liquid water, heated by tidal forces as Saturn's gravity flexes and squeezes the moon's interior. And that ocean has the ingredients, water, energy, organic molecules, that could potentially support life. Not complex life, probably, but microbes, maybe. The old assumption was that you needed to be in the habitable zone, that Goldilocks distance from a star where liquid water can exist on the surface. Enceladus showed that you can have liquid water far from any star, as long as you have another energy source. Tidal heating works fine.
When Cassini's fuel ran low, NASA couldn't risk it crashing into Enceladus and contaminating that pristine ocean with Earth microbes. So they deliberately plunged the spacecraft into Saturn's atmosphere in September 2017. In its final minutes, it transmitted data about Saturn's upper atmosphere, doing science until the signal went dead. The mission team called it the grand finale, and many of them cried. 13 years with a spacecraft, you develop a relationship with it. And now, in the 2020s, the story has circled back to where the biggest dreams always pointed, sending humans beyond low Earth orbit again, for the first time since Apollo. NASA's Artemis program, built around the Space Launch System rocket and the Orion capsule, aims to return astronauts to the lunar surface. Artemis 1, an uncrewed test, launched in November 2022, sending Orion around the Moon and back over 25 days. The SLS, despite years of cost overruns and delays, performed well. Artemis 2 is planned to carry crew around the Moon, and Artemis 3 aims for a landing, using a SpaceX Starship variant as the lunar lander. Starship itself is the most ambitious rocket ever attempted. Fully stacked with its super heavy booster, it stands about 394 feet tall, taller than the Saturn V. Both stages are designed to be fully reusable. The entire vehicle is built from stainless steel, a counterintuitive choice that turns out to make sense because steel is cheap, easy to work with, and performs well at both cryogenic and re-entry temperatures. SpaceX has been developing Starship through rapid iteration, launching prototypes, watching them fail, learning, and trying again. The first integrated flight test in April 2023 ended with the vehicle tumbling and being destroyed 4 minutes after liftoff. The launch pad itself was badly damaged because SpaceX hadn't installed a proper flame diverter. They learned that one the hard way. But each test flew farther. By late 2024, SpaceX demonstrated the Super Heavy booster returning to the launch site and being caught by mechanical arms on the launch tower, a maneuver so audacious it looked like visual effects. And this brings us to where we are right now, in this strange and wonderful moment in the history of space exploration. The International Space Station, continuously inhabited since November 2000, is approaching the end of its operational life, with decommissioning planned for around 2030. Commercial stations are being developed to replace it.
The James Webb Space Telescope, launched Christmas Day 2021, is peering deeper into the universe than Hubble ever could. Its gold-coated mirror collecting infrared light from galaxies that formed just a few 100 million years after the Big Bang. India's Chandrayaan-3 successfully landed near the Moon's south pole in August 2023. Japan's Slim lander touched down in January 2024. Private companies are attempting lunar landings. The barrier to entry is lower than it has ever been. Not because space got easier, but because decades of accumulated knowledge and falling launch costs have opened the door wider. And here's where the story of the equation and the metal comes full circle, in a way that Tsiolkovsky and Goddard and even von Braun might have recognized. For decades, the prevailing assumption in the aerospace industry was that rockets were inherently expendable.
You built them. You flew them once. They either burned up or fell into the ocean. And you built new ones for the next flight. This was simply accepted as the nature of the thing. It was how every rocket since Goddard's had worked. The economics were brutal, but considered unavoidable. Each launch required manufacturing an entirely new vehicle, and the manufacturing cost dominated the price. But the equation said otherwise. There was nothing in the physics that required a rocket to be disposable. The engineering was hard, certainly, much harder than building a rocket that only needed to work once. Landing a booster means carrying extra fuel for the return trip, which cuts into payload capacity. It means restarting engines in flight, which adds complexity. It means building structures that can survive not just launch, but the stress of re-entry and landing.
It means developing precision guidance systems that can navigate a 150-foot tube of metal through the atmosphere and set it down on a platform smaller than a football field. SpaceX didn't invent the idea. The DCX project in the early 1990s demonstrated vertical takeoff and landing with a small test vehicle. The concept had been studied for decades, but SpaceX was the first to actually do it with a rocket that had delivered a payload to orbit and then returned to be flown again. And they did it through a process that the traditional aerospace industry found bewildering and sometimes infuriating. They embraced failure as a design tool. The early landing attempts were spectacular in their destruction. Boosters came in too fast. They ran out of hydraulic fluid for the grid fins. They landed at an angle and toppled. They hit the drone ship and exploded. Each failure was analyzed, understood, and used to improve the next attempt. SpaceX Apocalypse published compilation videos of their landing failures, set to dramatic music with captions like, "How not to land an orbital rocket booster." The message was clear. Failure wasn't shameful. It was data. This was a profoundly different philosophy from the way NASA or traditional aerospace contractors operated, where failure was career-ending and every mission had to succeed. The SpaceX approach was closer to the way software companies develop products. Build fast, test, break, learn, rebuild. The aerospace establishment was skeptical, then grudgingly impressed, then scrambling to keep up. By the mid-2020s, the Falcon 9 has become the workhorse of the global launch industry. It has launched thousands of Starlink internet satellites into orbit. It has carried astronauts to the space station. It has sent commercial payloads for companies and governments around the world.
Individual boosters have flown more than 20 times each, a vindication of the reusability concept that would have seemed like science fiction just 15 years earlier. And the next step, Starship, is more ambitious still. Where Falcon 9 makes the first stage reusable, Starship aims to make the entire vehicle reusable,
both the Super Heavy booster and the upper stage. If it works, the cost of reaching orbit could drop by another order of magnitude. The implications for space stations, for lunar bases, for eventual missions to Mars are transformative. The equation hasn't changed since Tsiolkovsky wrote it. The exhaust velocity of chemical rockets hasn't improved dramatically. But by reusing the metal instead of throwing it away, you change the economics entirely. You don't need a better equation, you need better metal. Metal that survives the trip and flies again.
The James Webb Space Telescope, launched on Christmas Day 2021 and positioned about 1 million miles from Earth at the second Lagrange point, represents the other side of this story. Webb isn't about rockets or reusability, it's about the equation that hasn't been answered yet, the questions we don't know how to build machines to solve. Webb's 6.5-meter gold-plated mirror, made of 18 hexagonal segments that had to unfold after launch like a piece of origami, collects infrared light from the most distant objects in the observable universe. It's seeing galaxies that formed within a few 100 million years of the Big Bang, and what it's finding is puzzling. Galaxies that appear too massive and too mature for how young they are, suggesting that our models of early cosmic evolution may need revision. That's the frontier now. The equations are ahead of the metal again.
Theorists have ideas about what's happening in those early galaxies, about the nature of dark matter and dark energy, about the possibility of life on icy moons like Enceladus and Europa. But the instruments to test those ideas, the probes to visit those moons, the missions to drill through miles of ice to reach an alien ocean, those don't exist yet. The gap between what we know should be possible and what we can actually build is as wide as it's ever been. And that gap is where the next chapter of this story lives. The Artemis program represents a fascinating echo of the original equation-to-metal pattern. The plans for returning to the Moon have existed for decades. Various administrations have announced lunar return programs: Constellation under Bush, Artemis under Trump, continued under Biden, only to see them delayed by budget constraints, political shifts, and technical challenges. The equations for getting back to the Moon haven't changed since the 1960s.
The orbital mechanics are the same. The distances are the same. The physics of landing a vehicle on the lunar surface is fundamentally understood. What's changed is the industrial landscape, the cost structure, and the ambition. Artemis 3, the planned landing mission, will use a SpaceX Starship variant as its lunar lander, a vehicle larger and more capable than the entire Saturn V upper stage. The irony is rich. The company that started in a warehouse, that nearly went bankrupt after 3 failed launches, is now building the vehicle that will carry the next generation of astronauts to the Moon. The equation that almost killed SpaceX, the brutal economics of expendable rockets, drove Musk to reinvent the industry. And now that reinvention is enabling NASA's boldest program since Apollo. Meanwhile, the landscape of space exploration has expanded beyond anything the Cold War competitors imagined.
India's space program, ISRO, has landed on the Moon and sent a probe to Mars for less than the budget of some Hollywood films. China has landed rovers on the far side of the Moon, a feat that required placing a relay satellite at a Lagrange point to maintain communication. The European Space Agency's Rosetta mission rendezvoused with a comet and landed a probe on its surface. Japan has sent sample return missions to asteroids, bringing back grains of ancient material from the earliest days of the solar system. Private companies beyond SpaceX are building launch vehicles, space stations, and lunar landers. Rocket Lab, founded by Peter Beck in New Zealand, has been launching small satellites on its Electron rocket since 2018. Blue Origin, Jeff Bezos's company,
is developing its New Glenn heavy-lift rocket and has been contracted to provide a second lunar lander for Artemis. The commercial space station market is emerging, with Axiom Space, Orbital Reef, and others developing platforms to replace the aging ISS. And on the scientific frontier, the questions are bigger than they've ever been. The discovery of thousands of exoplanets, planets orbiting other stars, has shown that planetary systems are common in the galaxy. Some of those planets orbit in their star's habitable zone, at distances where liquid water could exist on the surface. The James Webb Space Telescope is beginning to analyze the atmospheres of some of these planets, looking for chemical signatures, oxygen, methane, water vapor, that might indicate biological activity. We're not quite at the point of detecting life on another world. The instruments aren't sensitive enough yet, but the gap is closing. The equations are on paper, the telescopes are being designed. The metal will follow.
And farther out, past the planets, past Voyager's lonely trajectory, questions are waiting that we barely know how to ask. What is dark matter? What drives the accelerating expansion of the universe? Are we alone? These are the equations nobody has written yet, the ideas that haven't arrived. And somewhere, in a university office or a research lab or a dorm room, someone is staring at a problem that the rest of the world hasn't even noticed, working through the math the way Tsiolkovsky worked through his, alone and uncertain, not knowing whether the answer will matter to anyone else or whether the metal will ever come. But if this story has taught us anything, it's that the equations do get written, and the metal does come. Sometimes it takes decades, sometimes it takes centuries, sometimes it arrives in the hands of people the dreamers never imagined, in countries that didn't exist when the math was done, for reasons that have nothing to do with the original vision. But it comes. Goddard's rocket flew for 2.5 seconds. 50 years later, his principles carried human beings to the moon. Tsiolkovsky's equation sat in an obscure journal for decades before anyone built a machine that could test it. And now every rocket that lifts off from Cape Canaveral or Baikonur or Wenchang or Sriharikota is governed by that same equation, derived by a deaf schoolteacher in a wooden house in Kaluga. And it's worth noting that the cost of space exploration, for all the billions of dollars spent, is remarkably modest in context. At its peak, NASA's budget consumed about 4.5% of the US federal budget. That was during the heart of the Apollo program in the mid-1960s, when 400,000 people were working toward Kennedy's deadline. Today, NASA's budget is less than half of 1% of the federal budget. The entire Curiosity rover mission, from concept to landing, cost about $2.5 billion, roughly the same as the production budget of a few Hollywood blockbusters. Voyager 1 and 2, which have been returning data for almost 5 decades and have explored the outer solar system in ways nothing else ever has, cost about $865 million total. Adjusted for inflation, that's less than what some cities spend on a single highway interchange. The argument that space exploration is too expensive has always been more a question of priorities than of actual cost. What people really mean when they say it's too expensive is that they don't consider it important enough to fund at a given level. And that's a legitimate position, but it should be stated honestly. The money exists. It always has. The question is whether the equation, the one that says we can go further and learn more, matters enough for the metal to get built. And if you step way back and look at the arc of all of it, from those Babylonian astronomers scratching observations into clay tablets, through Eratosthenes measuring the Earth with a stick and a shadow, through Newton describing orbits with a thought experiment, through Tsiolkovsky alone in his log cabin deriving the rocket equation that governs every launch to this day, through Goddard on his frozen Massachusetts farm, proving that a liquid-fueled rocket could actually fly, while the newspapers laughed, through the horror of the V2 and the moral ruin of the engineers who built it, through Korolev surviving the Gulag to put the first human in orbit, through Kennedy's impossible deadline and the 500,000 people who made it real, through the fire that killed 3 astronauts and the redesign that saved the program, through Armstrong flying the Eagle by hand with 15 seconds of fuel left, through the shuttle with all its compromises and its tragedies and its triumphs, through the kid in South Africa reading science fiction and deciding to build his own rockets because the price was too high and the pace was too slow. Through all of it, the same pattern keeps appearing. Someone figures out the equation, and then the world waits for the metal. Tsiolkovsky wrote the math, and Goddard built the first machine. Goddard built the machine, and von Braun scaled it up, at a cost that still haunts the story. Von Braun built the weapon, and Korolev built the vehicle that turned it into something more than a weapon. Kennedy declared the destination, and 400,000 engineers, technicians, programmers, seamstresses sewing spacesuits, welders bending fuel lines, built the road to get there. The shuttle was dreamed as one thing and built as another, and the gap between the dream and the machine cost 14 lives. SpaceX looked at the cost of reaching orbit and decided the equation was wrong, or at least that the metal could be built more cheaply, and then proved it by landing a rocket on a barge in the ocean. Every step in this story follows the same rhythm. The idea comes first, the hardware comes later, sometimes much later, and the people who have the ideas and the people who build the machines are almost never the same. That's not a flaw in the process, that's how it works. The equation and the metal need each other, but they arrive on different timelines, carried by different people, often separated by decades or continents or wars. The genius is in the handoff. The moment when one generation's impossible dream becomes the next generation's engineering problem, and some stubborn, brilliant, exhausted team of people sits down and solves it. And right now, tonight, that same process is happening. Somewhere, an engineer is running a simulation. Somewhere, a physicist is working through the math of a propulsion system that doesn't exist yet. Somewhere, a student is staring at an equation and wondering if it could be built. The problems ahead are enormous. Radiation exposure on long missions, the physiological effects of months in microgravity, the sheer distances involved, life support systems that need to work flawlessly for years, landing on Mars with human beings inside and bringing them home. Every one of those is an engineering problem, and this whole long story, tonight, everything we've walked through, has shown you what happens when stubborn people with good equations are given enough time. And you know what else is happening right now? The Voyager 1 spacecraft, the one we talked about at the very beginning, is still out there, still transmitting, still sending data back to Earth from beyond the edge of the solar system.
Its power source, a lump of plutonium-238, generating electricity from radioactive decay, is slowly fading. By the late 2030s, it won't have enough power to run any instruments at all. The signal will go silent. And Voyager will continue drifting through interstellar space, carrying its golden record, its collection of human sounds and images, deeper and deeper into the dark. In about 40,000 years, it will pass within about 1.5 light years of a star called Gliese 445 in the constellation Camelopardalis. It won't stop. It will keep going, essentially forever, unless something out there finds it. The equation that governs Voyager's trajectory was written by hand, in a wooden house, by a man who couldn't hear more than a century ago. The metal that carries it was built by people he never met, in countries he never visited, for reasons he never imagined.
And now that metal is further from home than anything human beings have ever created. Still traveling, still carrying a message, still proving that the distance between a dream and a destination is not as large as it seems. That's the story. The whole, long, beautiful, complicated story of how we learned to leave. And it's nowhere near over, but for tonight, it's enough. Enough to know that the sky you're lying under is the same sky that Tsiolkovsky watched from his window in Kaluga, and Goddard watched from his farm in Massachusetts, and Gagarin saw from orbit, thin and blue and infinitely precious. You're part of this story. Everyone who has ever looked up and wondered is part of this story. And the next chapter, wherever it leads, to Mars, to the moons of Jupiter, to places we can't even name yet, starts the same way every chapter has started. Someone writes the equation. And somewhere, eventually, someone builds the metal. So let your breathing slow.
Let the weight of the blanket settle. Let the thought of all those rockets and all those equations and all that stubborn, brilliant, imperfect human reaching drift through your mind like a signal crossing the dark between stars. You don't have to hold on to any of it. It's all still out there, all still happening, quietly, persistently, the way it always has. The engineers are at their desks. The equations are on the paper. The metal is being bent. Sleep well. The stars will still be there in the morning.